Hi all. In this lecture we will be starting one of the most important subject for electrical as well as electronics engineers, that is your network analysis. Now why is this most important? First of all, in GATE examination the weightage of this subject is simply 10 to 12 marks. Okay, that is why it is one of the reasons it is most important. Secondly, it is a prerequisite for most of our subjects. Like, if we talk about electrical engineers, then this subject will be a prerequisite for machine, power system, then measurement, power electronics. For electronics engineers, it is a prerequisite for analog electronics. It is a prerequisite for your EDC also. Not that much into ADC, but mostly for analog electronics you can say. Even in communication you can use this subject. Okay, because in communication you will be designing the analog modulators as well as demodulators. They will be based on electrical circuits. Now what is this network analysis all about? This basically focuses on analyzing different electrical circuits and developing techniques so that we can analyze them in a easier way. Okay. Now if you observe, on all sides we are surrounded by some or the other electrical and electronic equipments. Now those electrical as well as electronic equipments are composed of certain circuits, where each circuit has been designed to perform a certain function. And if you want to design such a circuit, before designing we must simulate it, we must analyze it in order to understand whether it is functioning in a desired manner or not. That is why this circuit analysis is very important. Because whenever we go for a design process always involves a simulation step. For simulation, you need to understand the basic analysis equation. Now, for any electrical and electronics engineer, the two corners foundation stone for the electrical engineering are EMT, that is electromagnetic theory, and circuit analysis. Okay. So in this lecture what we will do is we will study about the basics of circuit analysis so as to get acquainted with the terms that are generally used. You must have encountered these terms in one or the other way, but in this lecture we will gain a more clarity on these terms. What does each term mean? So the first term that we will understand is electrical circuit. What is the electrical circuit? It is basically connection of electrical components. Okay. What all electrical components can we have? We can have any sort of components like resistance, inductance, capacitance, diode, transistor, and so on. Okay. There can be any electrical components, and once you connect them in a certain manner, then it will be known as a circuit. Now when we design a circuit, our intention is that the current must flow in that circuit. Now what is the current basically? Current is the rate of flow of charge. Okay. Now this current must flow through this entire circuit in order to energize each and every component in the circuit. Is it fine? Now for the current flow, what is the necessary condition? There are two necessary conditions. One is a EMF source. What is EMF? EMF is the electromotive force which is responsible for energizing any sort of electrical circuit. And next is your closed path. For current to flow, we need a EMF source and a closed path. A closed path is basically a path that starts and ends at the same point. Like suppose if there are 2 points A and B, a path that will start at A and terminate at B, and then start from B then terminate at A will be a closed path. Current needs such kind of path to flow. Now one of these paths is always known as a forward path. Basically what is the purpose of forward path? To carry the current from source to the load. And the path that brings the current back is known as return path. Okay. So that means we need a forward as well as a return path for the flow of current. Is it fine? The bigger form of electrical circuit is known as a network. That means network comprises of many circuits like circuit 1, circuit 2, circuit 3. An example of this we can take from the any electrical device. Let us take an example of television. Okay. In this there will be multiple electric circuit like sensing the remote signal, okay. Then there will be a circuit to control the display. Then there will be a circuit which will be related to the power supply. Then there will be a circuit which will be connected to your D2H. This way there will be multiple circuits, and when all these circuits are connected together to work in a certain manner, then it will be known as a electrical network. Okay. So that is the difference between a circuit and a network. So a network is nothing but it is a bigger part of a circuit or a bigger form of a circuit. We can say a circuit is a subset of a network. Is it fine? So network is nothing but a large number of interconnected circuits. Another example you can take from a car. It has an accelerator which itself is a system in itself. Then a steering wheel. Then your music system is also installed. Okay. This way there will be multiple systems inside a single large system. Those systems will be called as subsystem, and network terminology, that entire system is called as network and subsystems are called as circuits. The next term that we'll understand is node and a branch. Now what is a node? A node is a connection point of two or more circuit elements. Okay. That is, if you see this point, at this point we have three elements 1, 2 and 3. That will be known as a node. Okay. Usually some places you will find two definition, node and a junction. There what they may have said that a node is the connection point of two elements and a junction is a connection point of two or more elements. That way they might have defined, but in general we define a node which has more than one elements connected to it. Is it fine? So node is a point of connection of multiple elements. Then what is a branch? A branch is a wire or any circuit element which connects two nodes. Like this 1 ohm resistor is a branch, this 3 ohm resistor is a branch, 2 ohm resistor is also a branch. Okay. So basically these terms are usually defined in graph theory, but they are applicable for any general circuit. A node is a connection point of multiple elements and a branch is the element which connects the two nodes. Okay. Now with a node we define something called as degree. Degree basically represents the number of elements that are connected to that node or number of branches. Like if you see here, we have 3 branches. So degree of this node delta equal to 3. Okay. And if there are only 2 elements connected, like if you see this node, it has a voltage source and it has a resistance. So delta equal to 2. If delta equal to 2, it is known as a simple node. And if delta is greater than 2, it is a principal node. Is it fine? Simple node. Greater than 2, we have principal node. So this is the classification for the node. The next term we define mesh and a loop. Basically loop is a superset of meshes. What is a loop? Which has the same starting and termination point. That is, it must start and end at the same point. What I was calling it as a closed path. Okay, like if you see here, suppose we mark these points as A, B, C, D, E, F. Then a mesh can be written as A, B, C, D, E, F, then again A. This is my loop. Okay, that is, it has the same starting as well as the ending point. Similarly, if you write this C, D, E, F, C, this is also a loop. Other A, B, C, F, A, this is also a loop. Okay, just you have to take care, there must be a path which starts and terminates at the same point. Is it fine? Now, what is a mesh? Basically, a mesh is a loop which does not have any loops inside of it. Now, if you see this loop, it has both these loops. Like this is one loop, other loop, and this third loop. This third loop has both these loops contained inside of it. So, it is a loop but not a mesh. Okay, but these two are mesh as well as loop. So, mesh is a subset of a loop, and it is a kind of loop which does not have any further closed path inside it. Is it fine? Now, how many meshes are there? That we will also understand. Mesh is also known as a fundamental loop when we will study about the graph theory. Now, usually number of branches in a network is represented by B. Number of nodes is represented by N. Now, the number of links we will study is equal to B minus N minus 1. That is B minus N plus 1. This is equal to number of mesh, or we can say number of fundamental loops. Okay, you can form as many loops as you may want, but the fundamental loops, basically what is the purpose of fundamental loops? They give us the independent equations for the circuit analysis. Independent equations as in, we will get a system of linear equations. Now, suppose we have 3 variables, then we need 3 equations to solve such a system. But if you have 4, 5, 6 equations, then the equations are redundant and they do not convey any additional information. That is why this mesh or this fundamental loop gives me a set of independent equations that we can solve in order to determine the circuit parameters. Is it fine? So that is the purpose of this mesh. Remember, if you take any other equation except for a mesh, that will be dependent on the set of mesh equation. So all meshes are loops, but not all loops are meshes. Okay. The next term we define is called as planar network. As the name suggests, plane. Plane means two-dimensional. If any circuit can be drawn in 2 dimensions, that is on a piece of paper, then it is a planar network. And if it cannot be drawn on a paper, it needs 3-dimensional view, then it is non-planar network. Okay. Now let us take example for this circuit. As you may see, this branch is coming out of the paper, so it must seem to us that it is a non-planar network. But you can remove this branch from here and you can connect it like this. Now this circuit itself is drawn in a 2-plane or a 2-dimensional plane. That's why it is a planar network. Okay. Now, if there is some circuit like then is it a planar or a non-planar network? It is still a planar network. How? You can rub this branch and you can connect it like this. Okay. Now this is drawn in two planes, so it is a planar network. Is it fine? Now suppose we connect another network here like a voltage source, and I want to connect this terminal via resistance to this. Now this cannot be drawn in two dimensions. We have to use a three-dimensional view. So it is a non-planar type of network. Okay, because these two branches cannot be separated. So that is how you categorize a planar and a non-planar network, one which can be drawn in a plane and one which cannot be drawn in a plane. Is it fine? Moving on to the next definition, we have linear and non-linear elements. Up to now, we were studying about the characteristics of a circuit or a network. Now we are talking about the elements used in that network. First of all, what is linearity? This definition is also used in reference with the signals. Linearity requires two principles or two conditions. One is called as homogeneity and other is called as superposition. Now, if there is any system in which we input the signal xt and we get output yt. If you input the signal kxt, that is multiplied by a constant, and the output comes as kyt, then it is known as homogeneity. But if input is x1t, output is y1t. Input is x2t, output is y2t. If you input x1t plus x2t and we get the output as y1t plus y2t, then it is known as superposition. That is, when we have multiple inputs, then we will superimpose those inputs and the output will be superposition of the individual outputs. That is the condition for superposition. And when these two conditions are combined, what we get is a condition for linearity. What is the condition for linearity? The condition for linearity is, if we apply the input ax1t plus bx2t, we must get the output as ay1t plus by2t. That is, a linear combination of inputs will yield the linear combination of individual outputs with the same coefficients. These coefficients must be same. Is it fine? That is the condition of linearity. Now, what kind of circuit elements are linear? The circuit elements that are linear is capacitor, inductor, resistor, transformers. These elements are linear. Why? Because they have a linear relationship between voltage and current. Because when we talk about the input and output, usually in case of any element or any circuit, the cause in case of electrical circuits is EMF. Okay? Cause is EMF, effect is current. So if there is a linear relationship between EMF and current, then it will be linear, otherwise it will be non-linear. Like if we take the example of a diode. In diode, the diode current is given as reverse saturation current e raised to the power Vd by nVt minus 1. As you can see here, diode current is exponentially related to diode voltage. So it is a non-linear element. Okay. So most of the semiconductor devices behave as non-linear element. Okay. And some of the linear devices even in semiconductor is a metal semiconductor junction or a ohmic contact. Okay. Actually, when we combine a metal and a semiconductor, two kind of contacts can be there: ohmic contact and as well as a Schottky junction. So ohmic contact is a linear junction and Schottky is a non-linear. Okay. Next type of elements are active and passive elements. Now what are active elements? Active elements actually use biasing, and thus they can amplify the signal. That is, there are two inputs in case of active elements. One is your biasing, one is your signal input. Now what these active elements usually do is they extract power from the biasing supply and then they supply that power to the input signal in order to increase its level. Okay, so they will increase the level or they will increase the strength of the signal by drawing power from the supply. Whereas passive elements do not draw any power from the supply and hence they cannot increase the power in the signal. What kind of elements are active elements? These are BJT, op-amp, such kind of element. So wherever you see any kind of biasing being applied for the circuit to operate, it will be a active element. What kind of elements are passive? The elements passive are R, L, C and diode. These elements do not require any biasing to operate and they can operate directly. Is it fine? So this is the difference between active and the passive elements. So you can also say that active elements will supply energy, whereas passive elements will absorb energy. Next is bilateral and unilateral element. In bilateral circuit, the property of the circuit does not change with change in direction, like in case of resistor. In case of resistor, V is equal to IR, doesn't matter whether the current flows from left to right or from right to left. Okay, these sort of elements are known as bilateral. Examples: R, L, C. These all elements do not depend on the direction of current flow or the direction or the polarity of the voltage across the element. Whereas if you take the case of a diode, when we talk about a diode, diode is basically a unidirectional element. That is, the current can only flow in a diode from anode to cathode. Okay, current can never flow from cathode to anode and hence its property will change with the change in direction of current. If the current flows from anode to cathode, it behaves as a resistance, or sometimes you also model it as a voltage drop. Okay, we usually consider a voltage drop of 0.7 volt. Whereas if current flows from cathode to anode, then it is treated as a open circuit. That is, we assume that current is 0. That is how the properties change when we change the direction of current. The next category is distributed and lumped element. Now in distributed elements, we actually cannot express the properties of the element in terms of its terminal condition. What are the terminal conditions? An element usually has 2 terminals and sometimes 3 terminals. Like a resistance, it has 2 terminals A and B. Now if you can express the element in terms of just the terminal voltage and the terminal current, that is V equal to IR, then it is known as a lumped element. Okay, whereas if it cannot be expressed in such a relation between the terminal voltage and terminal current, then it is known as a distributed element. Okay, then in that case we have to analyze the current and voltage at each point inside that element. Like even a resistor can be made of a conductor. Okay, but we need to know the voltage and current at just the ends, not at what is the voltage at midpoint, what is the voltage at quarter of the length. That is why it is modeled as a lumped element. But when we talk, let us take an example of long transmission line. Then we model it as distributed element. In distributed element, we define the voltage as a function of x, which is VR cos h gamma x plus IR ZC sin h gamma x. Okay, no need to memorize this equation, just I am taking as an example. So as you can see, voltage is modeled as a function of distance. That is why we are just not interested in the terminal voltage, but voltage and current at each and every point of the element. Those sort of elements are known as distributed elements. Is it fine? So mostly when we will be dealing with the circuit analysis, we will be taking care of lumped elements and we won't be going into the distributed analysis or the distributed elements. Why? Because to analyze distributed elements, you need to use the differential equations. Okay. That is why earlier also I told you the two foundation stones of electrical engineering is EMT and circuit analysis. Because when you go into the distributed elements, there you have to take care of the electric as well as magnetic field. The next sort of elements are known as time variant and time invariant. Now, suppose if resistance R is a function of time, then it is known as time variant. Okay, that means property of an element will change with change in time. Actually, this happens. How? This is known as your aging effect. As the age of an element increases, its performance also varies. Like you see in case of anything, like you see in case of your TV remote. As the age of the remote or the cells increases, their sensitivity or the sensitivity of the television towards that remote signal reduces. Okay? Because the power that it transmits will go on decreasing as the time increases. Okay? So if it is not transmitting the signal of the same level, it will be difficult for the television to sense that signal and act upon it. That is why in every case there is a aging effect. With increase in age, the parameters of the circuit will change. Such sort of elements are known as time variant. But in our course on circuit analysis, we will consider the time invariant elements. That is, resistance will be constant. If we are talking about inductance, it will be constant. If we are talking about capacitance, it will also be a constant factor. Okay? Because when we are analyzing a circuit, we are analyzing it at an instant. Okay? So if we are analyzing at an instant, there is no aging effect because we are not analyzing it over a period of time. I am not saying find out the current after 1 year. Okay, because in 1 year the value of element may itself change. Here we are only interested in your instant, like find the current at t equal to 0, 1 second or 2 seconds. At that instant the value cannot change. Is it fine? Next, let us discuss the elements that are used in circuit analysis. The first of them is the resistance. Now what is the resistance? Basically, resistance is an inherent property of any conductor by which it opposes the flow of current. Okay? Remember, it opposes current. Now it is analogous to inertia in your mechanical domain. What is inertia? It is the inherent property of a body by which it opposes the change in state of a motion. Like if there is a heavy element, if you try to move it, you will have to apply more force because there is more opposition. Similarly, in a circuit, if the resistance is high, we have to apply more voltage to circulate the same amount of current. It is analogous to your mechanical system. In a heavy element, more force is required for the same amount of displacement. Similarly, in an electrical element, higher resistance implies more voltage is required to circulate same amount of current. That is, it opposes the flow of current. It is the inertial property of any conductor or any electrical element. Now, usually we model the resistance as a linear relationship between the voltage and current. That is, if we draw a VI curve, the slope is modeled as resistance. And as I told you, we will consider it as time invariant. That is, Vt is equal to It into R. Okay, resistance is not considered as a function of time. Now if you take Laplace transform on both sides, Vs is equal to Is into R. That is, the ratio of the Laplace transform is equal to R. Usually the ratio of Laplace transform is known as transfer function. So the transfer function of a resistance is equal to the value of resistance, that is R. Here I am assuming the input is the voltage and output is the current. Okay. And in terms of sinusoidal excitation, we will study later on that we will model the voltage and current as phasors. There also V is equal to IR. Due to the resistance, the current and the voltage will be in the same phase because it is a constant factor. It does not provide any phase shift. Now what is the power in the resistor? Now the power is the rate of work done. That is dW by dQ. If we apply chain rule, dQ by dt. Now work done per unit charge is actually the potential and dQ by dt is current. So in electrical circuits, power is equal to voltage into current. In our case, voltage into current will come out to be I square R, or we can say V square by R. How? You will substitute the value of V as I into R. So you will get I square R. What about the energy? To determine the energy, actually power is the time rate change of energy. Power is actually dW by dt. So what is the work done or the energy stored? P dt, that is integral I square R dt. Okay. Usually what we do is, if you want to calculate average power, how to calculate average of any quantity? We will take 1 by T integral I square R dt. So since R is constant, it is taken common, 1 by T integral I square dt. So it is equal to I RMS square into R. So whenever we have a time varying current, that is the current is following a function of time. Let us say current is equal to sin t. So it is a function of t, then you have to use the RMS value of current in order to determine the average power loss in the resistor. Okay. And you can also write this expression as V RMS square upon R. Now basically what does the resistance do in terms of power? Usually the working of a resistance is to convert the electrical energy, this energy that we are determining, into heat. Okay. So do not think that resistance dissipates the power. It is not like that. Resistance converts electrical energy into heat energy. It is not necessarily dissipating the power. Why? Because what happens, suppose we are using a heater. Then there is a resistive element which will heat up the surroundings. That energy is actually being utilized by us. It is not being wasted. So resistance does not necessarily waste the power. If it is a part of the load, it is actually consuming power and giving us out the heat energy. But if it is a parasitic resistance, that is, it is not a part of the load or it is undesired, then actually it is wasting the power. Like suppose I am transmitting power from source to the load by means of transmission lines. The resistance of the transmission line will cause the power loss from the supply to the load. That resistance is undesirable. But if at the load end you have connected a heater, that resistance is desirable because it is giving you the heat energy which you can utilize in order to even cook food. That is the basic principle of your induction cooker. It utilizes electrical energy and converts it into a heat energy in order for you to cook food. How is that energy wasted? That is actually being utilized. The next parameter that we study is inductance. Basically, what is inductance? Inductance is a property by which an element opposes the change in current. Resistance opposes flow of current, inductance opposes change in current. That is, if ever a constant current is flowing through an element, that is the current is not changing, then inductance does not come into picture. Okay. So in case of constant current, inductance has no role. Inductance is usually we are considering here as self-inductance. Self-inductance means when we apply a voltage or a current to the coil and EMF is induced in the same coil. That is known as self-inductance. That is, A coil is responsible for inducing the EMF within itself. It is known as self-inductance. That is why it is being represented by L. Okay. Now with inductor we associate the concept of flux linkage. That is the amount of flux linking a coil, Li. And by Faraday's law, EMF induced is d phi by dt. Since inductance is time invariant, it will be L di by dt. That is the voltage across the inductor, that is L di by dt. And it is represented like this in terms of a coil. Okay, this is the current, this is the voltage. Is it fine? Now, if you want to go into the Laplace domain, to go into the Laplace domain, we will take Laplace transform both sides, Vs, L. Laplace transform of derivative is S into Is. Here we have assumed 0 initial condition. That is, Vs upon Is will be equal to S into L. So in Laplace domain, inductor is modeled as S times the L. Is it fine? And how to determine the current in the inductor? It will be 1 by L integral V dt. Here also if you take Laplace, Vs upon S. So we are getting the same relation. So that is how you model a inductor. Now let us understand the power and the energy in a inductor. As I told you, power in electrical circuit is product of voltage and current. So voltage is L di by dt into current is I. That is Li di by dt. Now if you want to determine energy, you will integrate p dt. Now this power is known as instantaneous power because we are taking current as a function of time. So this power will also vary with time. So it is Li di by dt into dt. That is, I can take L common, I into di. If you integrate I with respect to di, it will be half I square. Half L I square. That is the energy stored in a inductor coil. Okay. Now, if we take a DC current, that is I is equal to constant, then what is the voltage across the inductor? L di by dt will be 0. What is the instantaneous power in the inductor? That is 0, due to which energy is constant equal to half L I square. That is, energy, inductor does not store any more energy if you are giving a DC excitation. Okay. Now, usually inductance follows the Faraday's law, or you can even say it follows Lenz's law. What is Lenz's law? That effect opposes the cause. Now, here as you can see, due to the change of current due to di by dt, voltage is being induced in the inductor. This voltage will oppose the change in current. That is why I told you earlier, inductance always opposes the change of current. Okay. It is actually known by the name magnetic inertia. Just now I told you, inductor is associated with the flux linkages. Whenever the flux is linking with any type of element, then that flux cannot change instantaneously. That is your magnetic inertia. If flux cannot change instantaneously, so is the current. So in an inductor, current can never change instantaneously. It is also known as a current stiff element. That is, we cannot cause the current to change instantaneously. Suddenly the current cannot change. Is it fine? So that is the basic property of inductor. That is, it will be used when we will be studying transient analysis, that current at any instant cannot change in any inductors. And when we talk of a practical inductor, now a inductor is nothing but a coil. A coil will be formed by means of a conducting material. A conducting material has a property which we studied just now, that is a resistance. So a practical inductor is modeled like a resistance in series with a inductor. Okay. That means when we talk of a practical inductor, some part of the energy will be converted to heat and some will be stored in the inductor. How does the inductor store energy? It stores this amount of energy, half Li square, in its electromagnetic form. Remember, magnetic energy is always a stored form of energy. Okay, that is, it will store the energy in form of the current flowing through the inductor coil, and it will store that energy in the magnetic domain. There are various domains for energy, like electrical domain, in which we talk about the resistance energy, magnetic domain in terms of inductor, and mechanical domain in which we talk about the torque, or we can also talk about inertia. Okay, what is the practical application of inductors? They are used in filters, compensators, current limiting reactors, in communication as well as power system. In power system, current limiting reactor means whenever there will be a fault, an inductor will limit the amount of current flowing through the fault. Okay, filters, they will be used in LC filter, and they will be filtering out the noise. Like when you are talking or when there is a communication channel, then the noise must be filtered out so that the signal can easily be transmitted. The next element is capacitance. As the name suggests, capacity, it is basically a property of a system by which it has some capacity of storing charge. So it stores some charge. Okay, that is meant by capacitance. Capacitor is a device which stores a charge. Capacitor is nothing but it is a combination of two parallel plates laid out at some distance d. That is your capacitor. One plate will store a positive charge, other will store a negative charge. Now, capacitance is basically storing energy in electrostatic form. As I told you, inductor stores energy in electromagnetic form. It is storing in terms of electrostatic form. Now, what is electrostatic and what is electromagnetic? In electromagnetic, basically we are dealing with magnetic fields. In electrostatic, we are dealing with the electric fields. Now, the charge stored in an inductor is C into V. If you want to find the current, you will take dq by dt. As I told you, capacitance is time invariant. It will become C dV by dt. That is the current through the capacitor. What about the voltage of capacitor? 1 by C integral I dt. That is your voltage across the capacitor. If we take the Laplace domain both the sides, then current in Laplace domain derivative will be S times SC Vs, or we can say Vs is Is upon S into C. That is your voltage and the current in the capacitor for the case of Laplace domain. Is it fine? Now let us find out the power in the capacitor. As I told you, power is nothing but V into I. So that is, I can be written as C dV by dt, V into C dV by dt. That is C V dV by dt. That is your instantaneous power. What about the energy? Integral P dt, integral CV dV by dt into dt. We can take out capacitance common, V dV. Since the integration of V with respect to V itself will be half V square, so it becomes half C V square. That is the energy stored in the capacitor. Okay. Now, when you have DC excitation, or if you take the voltage as constant, if the voltage is constant, then dV by dt is 0. So current is 0. That is known as the steady state condition. Because when the voltage is constant, it means the charge is constant. So we are not storing any more charge on the capacitor. The charge on the capacitor has become steady. It is not changing. That is why the current is 0. Okay. As I told you, capacitor allows the storage of charge. Now, the charge cannot change instantaneously. The amount of charge stored cannot change instantaneously. That is why the voltage of the capacitor cannot change instantaneously. No sudden change in voltage. Okay, because if you are changing the amount of charge on a capacitor, it will take certain time. So that is why it does not allow sudden change of voltage. Similarly, inductor does not allow sudden change of current. Now, usually what we do is between the two plates of capacitor we place a dielectric. What is meant by dielectric? It is basically a insulator. But still why it is called as a dielectric? Because in a dielectric, if you take a atom, it will have nucleus and electron. If you apply a electric field, positive charge goes in the direction of electric field, negative charge opposite to it. And when the positive and negative charges are separated, it becomes a dipole. Now, basically for the current conduction we need free charges, but still though the positive and negative charges have separated from each other, there is still no free charge for flow. If there is no free charges that can flow in the conductor, then it is still a insulator, but due to dipole it is called as a dielectric. A dielectric is nothing but an insulator which has dipoles induced in it on application of the electric field. Now, if you change the orientation of electric field, that is if I reverse the direction of field like this, then positive will be here, negative will be here. That means if you can see, dipole has rotated by 180 degree. Now to rotate the dipole by 180 degree, we need some energy which is known as dielectric loss. Okay. So dielectric loss is nothing but the energy that is lost in order to rotate the dipole or to change the orientation of a dipole. So usually dielectric loss has two components. One is your leakage component, because no insulator is perfect. It will allow some current to flow through the insulator, due to which there will be some losses. That is known as leakage current. Other will be the due to change in polarization, which is known as dielectric loss. Due to this losses, usually how we represent a practical capacitor? By a capacitor in parallel with a resistor. That is your practical model of a capacitor. This parallel resistor is indicating the dielectric loss in the capacitor. This is usually very high. Ideally, this must be infinite, so the capacitor will act only as a C. If the resistance becomes infinite, it will become open. Okay. So that is basically how you model a capacitor. Now both capacitor and inductor are linear elements. Okay. Remember this point, both are linear elements. That is, both follow the principle of superposition and homogeneity. Again, both are bilateral element. Bilateral means they will allow the current to flow in any direction and voltage of any polarity across them. Okay. Then we can analyze inductor, capacitor as well as resistor in Laplace domain, time domain or frequency domain. There are three domains. In Laplace domain, we can form a general analysis in which we can do steady state as well as transient. But in frequency domain, we do the steady state analysis. In time domain, we can do the transient analysis. So Laplace domain gives us an advantage that we can convert a differential equation into algebraic. How? Because when you take the Laplace transform of derivative, it becomes S. Okay. So we can convert a differential equation into algebraic equation which can be solved easily. Also, Laplace takes care of initial condition, which is difficult to take care in terms of differential equations, because there you will have to find the constants of integration by the use of initial condition. But if you take Laplace transform, then those things are directly taken care of. Thus it is advantageous for us. So let me summarize what we have covered in this lecture. First, I told you about the circuit and network. Circuit is nothing but an interconnection of electrical elements through which the current can flow. Network is a bigger circuit in which there are multiple interconnected circuit. Then we saw node and branch. Then we saw mesh and a loop. Mesh is a special type of loop which does not have any inside loops. Then we saw type of element, linear, non-linear, time variant, invariant, unilateral, bilateral, active and passive elements. Then we saw the case of resistor in which V equal to IR, power is I square R, or we can say V square by R. Then we looked at inductor in which V is equal to L di by dt, or I is equal to 1 by L integral V dt. Energy stored is half L I square. In capacitor, current is C dV by dt, or we can say voltage is 1 by C integral I dt. Energy stored is half CV square. Okay, that is what we have covered in this lecture, and we have seen how do we model these parameters in Laplace domain. So in Laplace domain, inductor is equal to SL, capacitor is equal to 1 by SC. Okay, because here IS was equal to SC Vs, so Vs by Is is actually 1 by SC. Now if you take S equal to 0, S equal to 0 means time equal to infinite. Why it is so? Because time and frequency are reciprocal of each other. If time is infinity, that is your steady state, then S will be 0. So this is modeled as 0, this is modeled as infinite. That is short circuit and open circuit. When S is infinity, that is t is equal to 0, that is initial. This will be modeled as infinity, that is open circuit, and this will be modeled as 0, that is short circuit. So initially capacitor behaves as short circuit, inductor as open circuit, and finally inductor behaves as short circuit and capacitor as open circuit. Okay, so that is how you model the capacitor and inductor under steady state and the initial condition. So this is all about this lecture. In the next lecture, we will continue about the basics of the network analysis. Hi guys, in last lecture we started with network analysis, and first of all what we looked at is we looked at basic terminology associated with the networks. Like I told you what is meant by circuit, what is meant by network, what is a node, what is a branch, and then we moved on to circuit element. We saw the classification like linear and non-linear element, active and passive element, like bilateral and unilateral element. These sort of circuit elements we looked at. Then we moved on to types of circuit element, basic, like resistance. In resistance we saw V is equal to IR and power dissipated is equal to I square R. Then we moved on to inductance. We saw V is equal to L di by dt and energy stored is half L I square. Then we moved on to capacitance and we saw current is equal to C dV by dt and energy stored is half C V square. Okay, this up to here we covered in the last lecture, and in this lecture we will be moving forward from this and we will see some more circuit elements. So the next circuit element that we encounter is transformer. Basically transformer is a device which is used to step up or step down a alternating voltage. That is, we will either convert AC voltage to a higher or a lower AC voltage. Okay, it converts AC voltage into AC voltage, but what will change? Magnitude or amplitude changes. Okay, but what remains same is frequency. Frequency is constant. On both sides of the transformer, frequency of voltage remains same, just the amplitude of the voltage will change. Here N1 is the number of turns on primary, N2 is the number of turns on secondary. The left hand side winding of the transformer is called as primary, this is secondary. So number of turns of the coil at primary is N1, at secondary is N2, and this
turns ratio or these number of turns determine what is the change in amplitude of the voltage. That is V1 by V2 is equal to N1 by N2. Okay. The higher the number of turns in a winding, the higher is the voltage induced in that winding. But this ratio is inversely proportional to the current on both sides. It is equal to I2 by I1. Now if we see from this relation, we observe V1 I1 is equal to V2 I2. That means power on primary is equal to power on secondary. That is, though it may step up or step down the voltage, but power remains same when we go from primary to secondary or from secondary to primary. The power is same on both the sides. Only the currents and voltages change, and that too in a opposite ratio. If voltage is stepped up, that is voltage is increased, then current will be decreased, and if current is increased, voltage will be decreased. That means since the power is same in both sides of the transformer, this cannot be used as an amplifier. Okay, because it does not supply any additional power to the input power. Power remains same, so it cannot be used as an amplifier. Okay, remember this. Though it steps up the voltage, but it cannot function as an amplifier. An amplifier should essentially inject some power into the circuit. Next, let us see how we can inject power or current into the circuit. Up to now, what we have seen is circuit may consist of circuit element like resistance, capacitance, inductance, and transformer. But how to power those up? How to make some current flow through them? Then we have different power sources or different sources. Simply you can call them as sources as well as power sources. Now these sources are basically categorized into two parts. One is independent, other is dependent. Independent means their voltage or current does not depend on any other parameter. Okay. Like if I install a 5 volt cell or a 9 volt battery, then its current does not depend on current of any other cell or battery in the system. Okay, it is independent. So the supply voltage or supply current, if it does not depend on any other parameter, then it is an independent source. But if you think in terms of a transistor where the output current or output voltage depends on input current or voltage, that means it is a dependent source. The output parameters of this device depend on its input parameters. So independent source means the power supply, that is voltage or the current supply, does not depend on any other parameter, but if it does depend on any other parameter in this circuit, then it is a dependent source. Now independent source can also be of two types. It can be used to supply voltage, that is we can say voltage source, or it can be used to supply current. Okay. In voltage also there can be two things: practical sources or ideal sources. Okay, that depends on internal impedance. In current also same way classification, practical and ideal. In dependent we have four type of sources: VCVS, VCCS, CCVS, CCCS. These four type of sources are present in dependent sources. That is voltage controlled voltage source, voltage controlled current source, current controlled voltage source, and current controlled current source. These four type of dependent sources are possible. Here we see two parameters: how that source is controlled, whether it is controlled by a voltage or by a current. Then what parameter are you controlling? Are you controlling the current of the source or the voltage of the source? So this way we have four combination based on the controlling quantity and the controlled variable. Okay, here the controlled variable can be voltage and current, as well as controlling variable can be voltage and current. Okay, so let us look at these sources one by one. First is independent voltage source. Independent voltage source is something whose voltage is constant. It is unaffected by any other parameter. Okay, its voltage is constant. How do we represent such a source? We represent something like this. You may have seen. Okay, like 5-volt battery. Otherwise, what you can do is you can represent something like this. Just by positive and negative terminal, because a battery always has two terminals, one positive and one negative, because a battery supplies potential difference, and potential difference can only be present between 2 points. So we need two terminals for a battery. So this way we can represent by positive plate, negative plate, or just by plus and minus sign. When it comes to a AC source, the AC source is represented something like this. Okay, just a wavy curve is there in the positive and negative terminal, which illustrates that it is a AC source. Okay, now constant voltage source it can be, or it can be like something like 5 ut. Okay, that is, this voltage source is applied after t is equal to 0. Okay, just after t is equal to 0, this battery is connected in the circuit. This is my independent voltage source. Remember, independent voltage source means its voltage is constant. It does not depend on any other parameter. The voltage can be time varying also, like this. But here also the voltage is dependent only on time. It does not depend on any other parameter in the circuit. Like, suppose if we connect two resistances here, let us say R1, R2. This is VR2, voltage across R2. Now, if you see, the parameter in the circuit can be current, voltage across R1, voltage across R2. But this voltage is constant. It does not depend on any of these parameters. So, voltage should not depend on any of these circuit parameter. It may be dependent on time, but not on circuit parameters. That is the criterion of an independent voltage source. It should not have any dependency on any of the circuit parameters like currents and voltages. Next is dependent voltage source. Dependent voltage source means voltage source whose value depends on voltage or current at some point in the network. Like if we take, this is my independent source, let us say 5 volt. This is my resistance 1, resistance 2, let us say resistance 3. Now suppose the current going here is I. This is my dependent voltage source. It is shown in a block like this. Okay. Suppose I say the voltage of this source is 5I. Now if you see, the voltage depends on current flowing in R3. That is why it is a dependent source, because its potential difference depends on current in the network. So such kind of sources are termed as dependent source, and they are shown in this trapezoidal type of boxes, not a circular box. Now to control this voltage source, you can make a dependency on voltage as well as on the current. So we can classify into two categories: voltage controlled voltage source and current controlled voltage source. Here, like this is my current controlled voltage source, because this current I is controlling this source. But suppose if I give you like this, this is a source 4 into V3. Now here this V3 is controlling the magnitude of this voltage. Okay, this potential difference depends on V3. So it is a voltage controlled voltage source. Okay, the voltage of this source depends on voltage at some point in the network. It is a voltage controlled voltage source. Okay, next let us look at independent current source. Independent current source means the source current should not depend on any other parameter in the network. Now how do we represent a current source? It is represented by a arrow, because current always has a direction of flow. Either it will be flowing into a node or it will be flowing out of a node, but it will always have some direction. That is why we show this arrow to represent the direction of flow of current. Here let us say I is equal to 5 ampere. This is my current. So this current should not depend on any other parameter in the network. This can be something like this. Okay, or it can be something like this. It can depend on time, but it should not depend on any other parameter in the network. Same criterion as with voltage source. The only difference is it is supplying a current. A voltage source applies a potential difference, and the difference lies in the representation. There we show positive and negative terminal. Here we show direction of flow of the current. Here the direction is upwards. Similarly, the next is dependent current source. Dependent current source again means that the value of this source or the magnitude of current will depend on some parameter in the network. It will be represented by a trapezoidal box only. Trapezoidal box guarantees it is a dependent source, but here we will show an arrow because it is a current source. Now suppose I say I is equal to 4 V3, then it will be a current source which is controlled by a voltage. So it will be voltage controlled current source. Otherwise, if I take something like this, I is equal to 2 I2, it will be a current controlled current source. Okay, this current source is being controlled by some current. So that is how we classify the voltage and the current sources in the network. The only difference between that I told you between practical and ideal is for ideal voltage source, in an ideal voltage source, internal impedance R is 0, and ideal current source R is infinity. Okay, but when it comes to practical sources, how does a current and a voltage source look like? A voltage source will be something like this. This is V, this is R. And a current source will be something like this. This is the internal impedance of this current and voltage source. So for ideal, here R should be 0. For ideal, here R should be infinite. This is the difference between ideal and practical sources. The difference lies in the internal resistance or internal impedance of the network or the source. Okay, and remember, whenever we are finding the Thevenin equivalent, we can only remove the independent sources but not the dependent sources. Dependent sources can never be removed from the system. Okay, so whenever we are using superposition or Thevenin and Norton, we have to treat dependent and independent sources separately. Okay, so this thing always must be kept in mind when we are using superposition theorem or Thevenin theorem or Norton theorem. Independent and dependent sources are different. Okay, they will be treated differently. Otherwise, if any other theorem you are using, you can treat them as same. So these sources are different. Okay, otherwise, if any other theorem you are using, independent sources and dependent sources can be treated identically. That is, you do not need to care whether this source is dependent or independent. But while calculating Thevenin equivalent, we generally short circuit the independent voltage source, open circuit the independent current source, but we do not touch the dependent sources. Remember this: short circuit independent voltage source, open circuit independent current source, but never touch the dependent source. This you must always keep in mind while calculating the Thevenin equivalent. Okay, so these are the type of sources that we generally encounter in our electrical circuit. Now, when we want to analyze the circuit, the basic method of analysis is the Kirchhoff's law. So there are two Kirchhoff's law, one of which is Kirchhoff's current law. What does Kirchhoff's current law states is the total charge entering or leaving a node should be 0. The sum of the charge that is entering a node or leaving a node should be 0. There should be no charge storage at the node. Suppose if we take a node like this, 3 elements are connected in this node, current I1, I2, let us say I3. It says the charge entering the node is Q1 plus Q2 and charge leaving is Q3. The charge entering should be equal to charge leaving. There should be no charge storage at the node. So this theorem is based on conservation of charge. Now if you differentiate both sides, it will be I1 plus I2 is equal to I3, or what I can say, I3 minus I1 plus I2 is equal to 0. That is, I am taking the entering current with a negative sign and leaving current with a positive sign. Usually in KCL we will take leaving current as positive and entering current as negative. Okay, so it just says sigma I leaving plus sigma I entering should be 0. Remember, whenever we are considering entering current, we will associate a negative sign with those automatically. So the net current through a node should be 0. The entering current should be equal to the leaving current. And this law applies to any lumped electrical circuit, no matter whether the elements are linear, non-linear, active, passive, time varying, time invariant, doesn't matter. For every type of element, it will be applicable, but the only condition is it should be a lumped electrical circuit. The parameters should not be distributed. Then this KCL can be applied to any node. Okay, so this is only applicable for lumped circuit. And what was the criterion for lumped? That we can characterize the element based on its terminal voltage and current. We do not need to distribute the parameters, or the parameters do not depend on the geometry of the element. They only depend on terminal voltage and terminal current. The other law is Kirchhoff's voltage law. It says in a closed loop the sum of voltages should be 0. In a closed loop, sum of voltage should be 0. Like I will show you how. Plus minus, let us say R, L, C. Okay. So let us say voltage is VC, plus minus R, L, C. Here current flowing is I. This is my voltage source V. So first of all, the convention. How do we take a voltage as positive or negative? So if you go from negative towards the positive terminal, I will take that as positive potential. But if we go from positive to negative terminal, I will take it as negative potential. Okay. So let us move clockwise like this. Here I am going from negative to positive, I will take positive V. Then I am going from positive to negative, I will take minus IR. Again I am going from positive to negative, I will take minus LdI by dt. Again I am going from positive to negative, I will take minus Vc. This should be 0. That is, sum of the voltages in a closed loop should be 0. Closed loop means we should end up wherever we started. So we started at this point and we came back to this point. In such a case, the net voltage should be 0. And remember, when we go from negative to positive terminal, we take it as positive potential, and when we go from positive to negative terminal, we take as negative potential. Okay, positive means we are going from negative to positive, negative means we are going from positive to negative. That is, going from positive to negative, we encounter a voltage drop. That is why I am taking negative. While going from negative to positive, we have a voltage rise, so I am taking a positive potential difference. Now usually potential is work done per unit charge. So it can be written as Wi by Q. That is sigma Wi equal to 0. That is, net work done should be 0, which implies that the energy of the system is conserved. So KVL is based on conservation of energy. Remember, KCL is based on conservation of charge. It says net charge through a node should be 0. That is, entering charge should be equal to leaving charge. There should be no charge storage at the node. KVL says net work done should be 0. That is, there should be no energy entering or leaving the system. Okay, the entire system energy is conserved. The net work done on the system is 0. Similar to KCL, it is also applicable for lumped circuit. Okay, doesn't matter whether it is time variant or invariant, active or passive, linear or non-linear, it is applicable for all type of lumped circuit. So these are the two Kirchhoff's law which are very helpful when we are analyzing any electrical circuit. Okay. Now let us see what happens if we combine two sources. Okay. Suppose I give you a voltage source and I give you a current source in parallel. Then if a voltage source and a current source are connected in parallel, it is equivalent to a voltage source. Okay, you can neglect the current source, you can replace it by just the voltage source. Remember this, when a independent voltage and current source are connected in parallel, the voltage is constant. The voltage across this terminal will always be constant. So you can replace it by a voltage source. Okay. Similarly, if we connect a voltage source, let us say like this, 5 volt, some resistance, then 4 ampere. Suppose we connect a sources in series. Now we know the current in this branch can only be 4 ampere. So we can replace it by the simply resistance in series with 4 ampere. Okay. We can neglect the voltage source here. We can directly take only the 4 ampere. So remember, whenever current and voltage source are connected in parallel, we treat it as a voltage source. Current and voltage source in series, we treat it as a current source. And we cannot apply KVL when there is a current source. We cannot apply KCL when there is a voltage source. Why is that? Suppose if we wish to apply KCL, then I take multiple resistances and here I take a voltage source. Okay. So I can say current I is here, but I am not sure about the current supplied by this voltage source. I am only known about the potential difference across this voltage source. I am not sure what amount of current does it supply. So I cannot apply the KCL here unless I know what current does flow through the battery or the voltage source. Similarly, when we are using a loop circuit like this, then I am not sure about the potential difference across this current source. That means I cannot apply the KVL. The current source can have any arbitrary amount of voltage across it. Similarly, the battery can supply an arbitrary amount of current. There is no limitation to the current supplied by the battery. Similarly, there is no limitation to the voltage across the current source. Hence, we cannot use KVL when we are using a current source. We cannot use KCL when we are using a voltage source. Now, let us see how we can employ these two laws, KCL and KVL, to analyze a circuit. The first method of analysis is called as nodal analysis. It is based on the nodes. Okay. Here we will find the node voltages. Hence it is called as nodal. So first step what we do is identify nodes. Okay. Identify all the nodes in the circuit first of all. Then one of that node should be assigned as ground node. Okay. We need a reference to calculate voltage of any node. So we will connect one node to the ground. That will be my reference node. Then we will use KCL at every other node. At rest of the node, we will use KCL to form the equation. Let me show you this by an example. Suppose this circuit is given to me. I need to write the nodal equation. So here we have 4 nodes A, B, C, D. So first step is I have to identify the nodes. I have identified all the 4 nodes. Now the next step was I have to assign one node to the ground potential, or we have to connect it to ground. So let me connect this to ground. I have connected here this to ground. I am left with 3 other nodes A, B and C. Now let us apply KCL at A. Okay. So here the voltage I am assuming VA, VB, VC. So the current, I will assume all the currents as outgoing like this. So sum of the current should be 0. The current in 2 ohm resistor would be VA minus VB by 2. Okay, potential difference upon the resistance. Current in 3 ampere branch is 3 ampere. It is also outgoing, hence it will be positive. Current in 5 ohm will be VA minus VC by 5. This also I have considered as outgoing. Current in 2 ampere branch is 2. These 4 branches are connected to this, and one more, this 1 ohm resistance. The current through the 1 ohm resistance would be VA minus 0 by 1. These 5 branches are connected to node A, and hence this sort of equation will form. Okay, by applying KCL at node A. Now, as I told you, we cannot apply KCL whenever there is a voltage source. So it is very difficult to apply KCL when there are node B and C. So what I do is I assume a current I here. Now let us apply KCL at B. Okay, I will again assume all the currents as outgoing. How to assume like that? Assume like this, all the currents as outgoing. So current in 2 ohm resistor would be VB minus VA by 2. It is always safe to assume that all currents are outgoing. Okay, then sum of the currents should be 0. Current in 3 ohm resistor would be VB minus VD, but VD is 0. It is connected to ground. So it will be VB minus 0 by 3. Then the current through the 5 volt battery is I. This should be 0. Next, let us apply it to node C. Okay, here this current is incoming I. I will consider these currents as outgoing. So current through this 4 ohm resistor would be VC minus 0 by 4. Current through 5 ohm will be VC minus VA by 5. Current through this 4 ampere branch is 4. It should be equal to incoming current, which is I. Okay, this sum of 3 outgoing current should be equal to the net incoming current, which is I. Now we can substitute this value into the previous equation. You can substitute I here. So what we will get is VB minus VA by 2 plus VB by 3 plus VC by 4 plus VC minus VA by 5 plus 4 equal to 0. This will be my second equation. This was my first equation. But here we have 3 variables, VA, VB and VC. So we need 3 equations. The third equation can be VB minus VC should be equal to 5 volt. This will be my third equation. Now you can simplify this equation and plug it into a calculator. What you will get is VA will come out to be minus 4.03, VB will come out to be minus 1.23, VC will come out to be minus 6.23. Okay, these will be the potentials that will come out if we solve these 3 equations. So remember, you have to form as many equations as there are number of node voltages, then plug it into the calculator. At most in an examination you will encounter 3 equations, because our calculator can solve only 3 linear equations simultaneously. Then when you find the node voltage, you can also calculate any current by using these expression. Like current in 4 ohm resistor is VC by 4. Current in 5 ohm is VC minus VA by 5. This way you can calculate any branch current also. So here first aim is to find node voltage, then using node voltage we can calculate any branch current. Okay, so this is the method of nodal analysis. Let's move on to the next analysis, which is called as mesh analysis. As the name suggests, mesh is nothing but a loop. So here we will apply KVL in a loop. So the first step is same. There we were identifying nodes. Here we will identify meshes. Okay. Then next thing is, there we assume node voltages. Here we will assume mesh current. Okay. With each mesh we will associate a mesh current. Okay. Last is KVL plus Ohm's law. You have to apply KVL plus Ohm's law to form equation, then solve those equations to determine the all mesh current. You can determine every mesh current by solving the KVL equation that you form. Okay. So let us see an example. Suppose this circuit is given to me. I need to find the power delivered by the voltage source. So first thing is, I must assume mesh current. Here there are three meshes. One is this. So I assume like this. This, let us say I3. This is one mesh. I assume a current anti-clockwise. Let us say I1. This is one mesh. I assume a current clockwise. Let us say I2. Okay. Three meshes are there. I have assumed three currents, I1, I2 and I3. Okay. One I1 is assumed as anti-clockwise. Other two currents I have taken clockwise. It is your choice. You can also take I1, I2, I3 all as clockwise. If your assumption is anywhere incorrect, that current will come out with a negative sign, which will show you that the direction you assumed was incorrect. Okay. So you can safely assume any direction, whether all anti-clockwise, all clockwise, some anti-clockwise, some clockwise, that depends on you. Okay. But if your assumption is wrong, the current will come out to be negative. So let us apply now KVL. For that, I need to know the voltages in each and every element. So let us first apply the KVL in this outer loop or the above loop in which I3 current is flowing. Okay. So current through this 1 ohm resistor will be this resistance. It will be how much? It will be I3 plus I1. Okay, and the direction of voltage will be positive, negative. Okay. Similarly, current in 3 ohm resistor would be I3. It will be like this, positive, negative. Current will be I3 like this. In this 1 ohm resistor, how much current will be? It will be positive, positive, negative. The current in this will be I2 minus I3. Okay, because I2 is flowing like this, I3 is coming like this. Okay, and always remember, in a resistance, when a current enters I, the terminals are like this. So in the direction of current, we will assign positive and negative terminals. Since I have assumed I2 minus I3, I have taken positive and negative like this. In this 2 ohm resistor, current is like this. So it will be positive, negative. I2 ohm will be I2. Similarly, in this I1 ohm, positive, negative will be like this. I1 ohm will be equal to I1. These will be the currents that will be flowing through these elements. Now we have to apply KVL. Okay. So let us apply KVL in the upper loop. Here we go from positive to negative. I will take minus I3 into 3. Then we again go from positive to negative. We will take minus 5. Then we go from negative to positive. We will take plus 1 I2 minus I3. Then we go from positive to negative. We will take minus 1 into I1 plus I3 equal to 0. So if you take the coefficient of I1, it will be minus I1, I2 will be plus I2, and I3 will be minus I3, minus I3, minus 2I3, minus 3I3, minus 5I3 will be equal to 5. This will be my first equation. Now let us find out second equation. Second equation we will apply KVL along this, because we cannot apply KVL along the current source. So the directions that we assumed were positive, negative, negative, positive, positive, negative, positive, negative, positive, negative. So let us apply KVL. So if we go from negative to positive, I will take plus 1 into I1. Then we go from negative to positive, again I will take plus 1 into I1 plus I3. Then we go from negative to positive, I will take plus 1 into I2 minus I3. Then we go from positive to negative, minus 2 I2. This should be 0. This is my second equation. Okay. Now for forming the third equation, if you see, current I1 is like this, I2 is like this. So what I can say is I1 plus I2 is equal to 10. I1 is like this, flowing upwards, I2 is also flowing upwards. These will be added and it will be equal to 10 ampere. This is my third equation. Here we assume three variable I1, I2 and I3. We have now three equations in I1, I2 and I3. If we solve, I1 comes out to be 20 by 3, I2 comes out to be 10 by 3 and I3 comes out to be minus 5 by 3. Here we needed to find the power delivered by the voltage source. So power will be voltage into current. In this voltage source the current is 5 by 3, this I3. Negative sign just implies that the direction is opposite, like this. Okay. And anyways, the battery will only deliver a current if current goes out of the positive terminal. Okay. Let me rub this and tell you this concept. If a battery is given and current comes out of the positive terminal, it delivers the power. Okay, and power will be taken as positive. If a battery is given and current goes into the positive terminal, then it absorbs the power and we will take P as less than 0. Now power will be nothing but voltage into current. Voltage is 5, current is 5 by 3. It will be 25 by 3. Now we assume that the current is like this, but current is coming negative, which means current is opposite direction. That is, it comes out of the positive terminal. So this battery delivers this power. So this power will be taken as positive. This battery is delivering the power. Let us summarize what we learned in this lecture. We first saw transformer, where we saw V2 by V1 is equal to N2 by N1 is equal to I1 by I2. Then we learnt about sources, dependent as well as independent sources. Independent are like this in circle, dependent are like this. Okay. Then we saw KVL and KCL. Then we saw nodal and mesh analysis. So this is the very basic type of analysis that you can do for solving a circuit. This is the most basic equations that you can form. Okay. In the next lecture we will proceed forward with how to connect different circuit elements and what will be their equivalents.
Hi guys, up to now we have seen some of the network elements. What were the network elements? These were the elements that were constituting a electrical network, like a resistance, inductance, capacitance, and a transformer. Okay. Then we have seen type of different sources like dependent sources and independent sources. In dependent and independent sources, we have seen two categories: current sources and voltage sources. Okay. Current sources supplied a constant current into the circuit, and voltage sources applied a constant potential difference in the circuit. Then we have seen how to simplify the circuit or how to analyze the circuit by Kirchhoff's laws, that is KVL, by which we apply mesh analysis. In mesh analysis, we find an independent set of mesh and then we form the KVL equations and simplify those equations in order to determine the loop currents. And by calculating loop currents, then we can determine any branch current in the circuit. Then we studied KCL, by which we applied nodal analysis. So at every node, we applied KCL in order to determine the node voltages. And in terms of node voltage, we can determine any branch voltage as well as any branch current. In this lecture, our focus will be on interconnecting the network elements and then representing those elements by a single equivalent element. Now, first type of connection is called as series connection. In series connection, what happens is, whenever two elements are connected, let us assume there is a voltage source. Then this is element number 1, element number 2. This is how they are connected in series. What is the criterion for series connection? Suppose I1 is the current here, I2 is the current here. Now if we apply KCL at this node, incoming current should be equal to outgoing current. That means current in both the elements is same. That is the criteria for series connection. Now how can you tell just by looking at the connection whether it is a series connection? For that you have to check that there must be a node which is connected to the two elements and not any other element. That is, if between the two elements, if there is a node which is only connected to these two elements, like suppose these are two resistors R1, R2. This is a node which is connected to only these two elements. Now if you connect it to another element R3, then this is not a series connection because it is connected to three elements. Okay. So that is how you identify a series connection. Now in series what happens is, if we apply KVL, okay, then V will be equal to V1 plus V2. Now V will be equal to IZ1 plus IZ2. Z1 and Z2 are referred to as impedances. Impedance in the sense whatever is the resistance offered by this element. Actually what happens when we will study about AC, then what we will do is we will represent even inductors and capacitors in terms of resistances, and that is known as the impedance. So impedance is the analog of resistance in the AC circuits. That means I into Z1 plus Z2. That means I can write it as I Z equivalent, where Z equivalent is a single element having an impedance equal to sum of the two impedances. So in series, impedances are directly added up. Now, if we talk in terms of Laplace domain, resistance, for resistance impedance is equal to R1, R2. So Z equivalent will be R1 plus R2. For inductor, in Laplace domain we saw SL1, SL2. So it will be L1 plus L2. Okay. So we can say equivalent inductance will be L1 plus L2. What about capacitance? 1 by SC1, 1 by SC2. So we can say 1 by SC is equal to 1 by SC1 plus 1 by SC2, or we can say 1 by C is equal to 1 by C1 plus 1 by C2. Okay. So that will be your equivalent capacitance. So that is how you combine the elements connected in series. So criterion for series connection, there must be a node, and then that node must be connected to only these two elements and not any other element. And what about the sources? Any two current source cannot be connected in series. Why? Because current source is a constant current. Now suppose I connect 2 ampere and 3 ampere in series. Then what will be the current across the series combination? It cannot be 2, it cannot be 3. Okay, that's why two current sources can never be present in series. Because the criterion for series connection is current must be same. If two current sources of different currents are in series, then how is it possible? Okay. But we can connect voltage sources in series because by means of KVL, the voltages will get added up. Next comes the parallel connection. In parallel connection, this is my voltage source. This is one impedance. This is second impedance. Okay. Now if you see, these two impedances are connected in a loop. And this loop consists only of these two impedances and not any other element. So if two elements are to be in parallel, then they must be a part of loop which does not contain any other element except these two elements. Now here the criterion is the voltage is same across both the elements. Okay, because suppose I consider it to be ground, the voltage of this will be V, this will also be V. So voltage of Z1 is equal to voltage of Z2 is equal to the supply voltage V. Now what is the current here? It will be the sum of two currents by KCL, I1 plus I2. Okay, that means I is equal to, what is I1? V by Z1. What is I2? V by Z2. And I will be V by Z equivalent, which means 1 by Z equivalent is equal to 1 by Z1 plus 1 by Z2. Now what about the resistance? For resistance, Z1 and Z2 are R1 and R2. So what is the relation? 1 by R is equal to 1 by R1 plus 1 by R2. What about inductor? SL1, SL2. That means 1 by L is equal to 1 by L1 plus 1 by L2. S will be cancelled from both sides. For capacitor, 1 by SC1, 1 by SC2. That is C is equal to C1 plus C2. Again S will be cancelled. So if you see, resistance and inductance follow the same principle in series and parallel addition, but capacitance follows the opposite principle. That is, the rules for series and parallel are just opposite for the case of capacitance versus resistance and inductance. Is it fine? Now, similarly, as we said that two current sources cannot be in series, similarly two voltage sources cannot be in parallel. Because in parallel condition, the necessary condition is voltage is same. Now, if you connect 10 volt and 5 volt in parallel, then that violates the basic condition for parallel connection. Okay. That means we cannot connect such sources in parallel. Okay. But current sources can be connected in parallel, and by means of KCL we can convert them to a equivalent current source. Next, when we come to series connection, we create a general rule how the source voltage or how the supply voltage is divided amongst different elements. So let me again draw the case for series connection. This is impedance Z1, impedance Z2. Okay. Don't get too much bothered by this term impedance. This is defined in AC circuits, but is a general term for resistance, inductance as well as capacitance. Here current is going I. This is V1. This is V2. Now what is V1? IZ1. What is V2? IZ2. Now I know I is equal to V by Z equivalent, and in series the Z equivalent is Z1 plus Z2. So what is V1? V Z1 over Z1 plus Z2. What is V2? V Z2 over Z1 plus Z2. Okay. That is V1 by V2 is equal to Z1 by Z2. So that is how the voltages are divided in series connection. Okay, they are divided directly proportional to the impedance they are measured across. If you are measuring the voltage across Zi, then the voltage will be Vi. Now, how to generalize this rule for resistance, capacitance and inductance? I know Z is directly proportional to R, or Z is equal to R for resistance. For the case of resistance, what will be the case? For the case of resistance, V1 will be equal to V R1 over R1 plus R2. What is V2? V R2 over R1 plus R2. What about inductor? Z is equal to SL. So if you see V SL1 SL1 plus SL2. Now S is cancelled in numerator and denominator. L1 plus L2. What about V2? Similarly, VL2 over L1 plus L2. That is, resistance and inductance follow the same rule for voltage division. What about capacitance? It is 1 by SC1. Okay. Now that will be coming out to be V into C2 over C1 plus C2. Similarly, V2 will be V C1 over C1 plus C2. So if you see, V2 is proportional to C1 and V1 is proportional to C2. That is, it is just the opposite. Okay, in case of capacitor. So remember, the rules remain the same for resistor and inductor, but they do change for the case of capacitors. Similarly, when we talk of parallel connection, the supply current will be divided into different impedances. That is, if I take a current source I, then suppose there are two impedances Z1 and the other impedance Z2. Then this current I will be divided into two parts, I1 and I2, such that I1 plus I2 is equal to total current I. Now I1 is equal to V by Z1, I2 is equal to V by Z2. I know that V will be equal to I into Z equivalent, that is I into Z1 Z2 over Z1 plus Z2. How it is Z equivalent? Because I told you 1 by Z equivalent is 1 by Z1 plus 1 by Z2, which is Z1 plus Z2 by Z1 Z2, which implies Z equivalent is Z1 Z2 over Z1 plus Z2. That is the value that I am using here. Now, if we substitute this value, then what is I1? Z1 will get cancelled out, Z2 over Z1 plus Z2. I2 is Z1 over Z1 plus Z2. Now, if you observe here, in current division, we have to use the other impedance. That is, if I am calculating I1, I have to take Z2, and if I am calculating I2, then I have to take Z1, which is just the opposite of the voltage division. In voltage division, for calculating V1, we were using Z1. For calculating V2, we were using Z2. Okay, so the rules change in this case. So if we write down the equations for resistance, inductance and capacitance separately, because these are the general equations for resistor. Sorry, here we are determining I1 and I2. What is I1? I R2 by R1 plus R2, because impedance is proportional to resistance. It will be I R1 by R1 plus R2. What about for inductor? Same rule. I L2 by L1 plus L2. I L1 by L1 plus L2. What about capacitor? It is inversely proportional to capacitance. 1 by C2 over C1 plus C2, that is I C1 over C1 plus C2. It will be I C2 over C1 plus C2. That is, I1 is proportional to C1, I2 is proportional to C2. So as you can see here, the rule for capacitor is again the opposite of the inductor and capacitor. So in voltage division, Vi is proportional to Zi. In current division, Ii is proportional to 1 by Zi. Okay, that is how you have to divide the current and voltages. Next type of circuit technique that we will study is the star delta transformation. Now whenever three impedances or three elements are connected, usually there are two type of connections defined. One is a delta connection, other is a star connection. In delta, actually all the three elements are connected in a closed loop, that is one after the other. Whereas in a star connection, all the three elements have a common node, which is also known as the neutral. Okay, so there is no neutral point in case of delta connection. Now suppose I want to convert from this delta connection to star. That means I want the impedance to be connected like this. Then if you see Z1, Z1 will be connected between ZA and ZC. So Z1 is given by ZA, ZC over ZA plus ZB plus ZC. Now Z2, it is connected between ZA and ZB. ZA, ZB over ZA plus ZB plus ZC. What about Z3? Between ZB and ZC? ZB, ZC, ZA plus ZB plus ZC. Now if we write for the case of resistances, R1, RA, RC over RA plus RB plus RC. Then R2, RA, RB over RA plus RB plus RC. R3, RB, RC over RA plus RB plus RC. That is the case of resistor. Inductor will also follow the same rule. That is, if we write in terms of inductance, L1 will be equal to LA, LC over LA plus LB plus LC. What about L2? LA, LB over LA plus LB plus LC. What about L3? LB, LC over LA plus LB plus LC. In case of capacitor, this rule will get reciprocal because impedance is proportional to 1 by capacitance. So C1, 1 by CA, 1 by CC over 1 by CA plus 1 by CB plus 1 by CC. So this will come out to be how much? CB over CACB, CBCC, CACC. Okay, that is how it will come out. That means you have to consider the capacitance which is not included in 1. Like if you see 1, it is connected between A and C. So here we are getting B. Similarly, C2 will come out to be CC, CACB plus CBCC plus CACC. Actually, this should be 1 by C1. This should be 1 by C2. Similarly, we can determine 1 by C3. So 1 by C3 will be 1 by CB, 1 by CC over 1 by CA plus 1 by CB plus 1 by CC. Okay, that will be your 1 by C3. So if we take the reciprocal, I can write down CA as CACB plus CBCC plus CACC over CB. Okay, that means first you have to take the combination of all the capacitances and then you have to divide whichever is not included. Like for Z1, it is lying between A and C, so you have to take B. Similarly, C2 will be CACB, CBCC, CACC divided by, for Z2, it is included between B and A, so it should be CC. Similarly, we can define C3. Now suppose all the impedances were equal. That is, let us say ZA equal to ZB equal to ZC. Then Z1 equal to Z2 equal to Z3 equal to how much? It will be Z into Z over Z plus Z plus Z. That is Z by 3. That is Z star is equal to Z delta by 3 in case of equal impedances. Now the reverse of this transformation also holds valid. That is when we want to go from star to delta. So we want to connect three impedances like this. Okay. So now if you see, when you will transform here ZB, how you will transform? First take all the combination, that is Z1, Z2, Z2, Z3, Z1, Z3. Now use the impedance which lies in the front, that is here. In front of ZB it is Z1. Then if you write down for ZA, again you will write all the combination Z1, Z3. Now you will use the impedance that is in front of ZA, that is Z3. For ZC, Z1, Z2, Z2, Z3 plus Z1, Z3. Now you will divide it by, what is the impedance in front of ZC? It is Z2. So that is how you transform from delta to star to delta. Okay. Now if you want to generalize these rules for resistance, inductance and capacitance, for resistance how it will be? RA is equal to RA-RB plus RB-RC plus RC-RA divided by, for ZA it will be divided by, sorry, this will be R1, R2 actually. For RA it will be R1, R2 plus R2, R3 plus R1, R3. Now the impedance in front of ZA is Z3, so we will divide it by R3. For RB it will be R1, R2 plus R2, R3 plus R1, R3. Now for RB we will divide it by, for RB the impedance in front is Z1, we will divide by R1. For RC, R1, R2, R2, R3 plus R1, R3 divided by divided by R2. Same way we can write for inductances. For inductances, LA will be equal to L1, L2 plus L2, L3 plus L1, L3 divided by, for LA it will be L3. LB, L1, L2, L2, L3 plus L1, L3. For LB we will divide it by L1. L1, L2 plus L2, L3 plus L1, L3. Here we will divide by L2. And the opposite we will follow for capacitance, 1 by CA by C1, C2, 1 by C2, C3, 1 by C1, C3 divided by 1 by C3. 1 by CB will be 1 by C1, C2, 1 by C2, C3, 1 by C1, C3 divided by 1 by C1. Similarly, we can write 1 by CC, 1 by C1, C2, 1 by C2, C3, 1 by C1, C3 divided by 1 by C2. So that is how you transform from delta to star and from star to delta. Is it fine? So these are the basic formulas that you must always remember. Now again we will take the case of equal impedances here. If impedances are equal, then Z delta will be equal to Z dot Z plus Z dot Z plus Z dot Z divided by Z, that is 3Z. So delta impedance is equal to 3 times the star impedance if the impedances are equal. Now there is another technique known as the source transformation technique. Now sometimes if you have voltage sources, okay, or if you have one voltage source and one current source connected in parallel, then if you need to combine those two, suppose I give you a circuit like this, and here I give you a current source. Now if I want to combine this, then it would have been better, since they are in parallel, if I could have both the current sources, then it will be easier to add. In that case, we will need to convert this voltage source into a current source. How do we do that is, suppose there is a voltage source in series with a resistance. Then what will be the current? If we short circuit these terminals, I short circuit will be V by R. So what we do is, we connect a current source equal to V by R, and we connect a resistance in parallel, that is equal to R, and this will be my equivalent. Now if you short circuit this terminal, the whole ISC will flow through this, so it will be equal to V by R. So the same condition will hold true here also. Okay, that is why this voltage source is equivalent to this current source. If you keep these terminals open, here the current is 0. If we keep these terminals open, no current will go here. That is under short circuit as well as under open circuit. Both are behaving identically. Next, we can convert a current source into a voltage source in a similar manner. So if a current source is given to me I in parallel with a resistance, then suppose this terminal is open, this I current will go here. So the voltage across this will be VOC, which is equal to IR. That is, open circuit voltage will be IR. So we convert it to a voltage source in series with a resistance IR R. Now if you see, if you do not close these terminals, it is open, then current here is 0. So the entire voltage will appear here, that is equal to IR. Now if we short these terminals, then the current here will be I. If we short these terminals, current here will be IR by R, that is equal to I. Hence both the systems are equivalent under open as well as short circuit. Then what is meant by this open or the short circuit? So in open circuit, actually there is no closed loop, and as I told you, current requires a closed path to flow. If there is no closed loop, that means there is no current. That is your open circuit. Is it fine? So in open circuit, the current is 0 at any two terminals. Like this, I can show you. If this is a current source, this is a resistance. And if you have another resistance here, but you haven't connected anything here, so it is open circuit. Is it fine? So what will be the resistance of open circuit? It is V by I. Since I is 0, the resistance of open circuit is infinite. Similarly, what about short circuit? In case of short circuit, actually, the two terminals or two nodes are connected via wire. Okay, if they are connected by a wire, then what will happen? It is known as short circuit. And in this case, if they are connected by a wire, they are directly connected, the voltage goes to 0. How? Suppose this is my voltage source with a resistance. If we want to short these terminals, we will directly connect them with each other. So the current here will be V by R. Okay. Now current in a short circuit or resistance of short circuit is equal to V by I. Since V is 0, so short circuit resistance is 0. Usually in practical, whenever there a short circuit happens, it happens by means of a certain conducting material. If there is a conducting material, it will have certain resistance. So actually the resistance is not directly equal to 0 even in the case of a short circuit. There will be some short circuit resistance or some short circuit impedance. Okay. So suppose I have connected a resistance here, let us say R dash, then you have to neglect this resistance because no current will go here. I R dash is 0. As we saw in the current division, I1 was equal to I Z2 by Z1 plus Z2. Okay. that is I by Z1 upon Z2 plus 1. So if Z1 is 0, current is entirely I. That means current tries to take the path of lower impedance. Otherwise, you can understand in terms of I1 by I2 is equal to Z2 by Z1. So it is inversely proportional to impedance. So it will try to take the path of minimum impedance. If you are giving it a path of zero impedance, that is the most ideal case. It will flow through that path. Is it fine? So that is how, even in the event of a short circuit, usually we neglect the load. So we do not consider our load whenever there is a short circuit in the system. Now let us look at a few problems on determining the equivalent resistance. If you see this type of circuit first of all, in which these 5 impedances or 5 resistances are connected in this manner. First you have to check it for a Wheatstone bridge in balanced condition. How to check? Let me call this as R1, R2, R3, R4, R5. If you see this kind of relation holding true, R1 by R2 equal to R3 by R4, or you can say R1 R4 equal to R2 R3. That is product of opposite branches being equal. This is 3 into 2, 6, and this is 3 into 1, 3. Okay. So actually this is 3 into 1. This is actually 6 here. It is wrongly printed. So that is 1 into 6 is equal to 3 into 2. So it comes out to be 6 on both the sides. That means it is in balanced condition. Okay. If it is in balanced condition, then you can remove this impedance 3. If we remove this, then the circuit that is left is like this. Now if you see 1, 3, 2, 6. 1 and 3 will be 4. They are in series. As you can see, only one node is common. This 2 and 6 are also in series. So like this. So what will be the equivalent resistance? These 4 and 8 are in parallel. 4 into 8 by 4 plus 8. That is 32 by 12, or we can say 8 by 3. Okay. So that is how you determine the equivalent resistance when both the circuits are not connected in parallel. Okay. Now suppose if it was not equal to 6, rather it was equal to 3, then what you would have done? Then it is not a Wheatstone bridge in balanced condition if it is 3. Because here 1 into 3 is not equal to 2 into 3. Then what to do is, you will convert this delta into star. Since here all the 3 are equal, Z star is equal to Z delta by 3. That is 3 by 3, which is equal to 1. So in star connection we will have 1 ohm resistances. Okay, that is 1, 2, 1, 1, 1. Okay. So this 1 and 1 are in series, that is 2. 2 and 1 are in series, that is 3. And here this will be 1. 2 and 3 are in parallel, plus 1, that is equal to 2.2 ohm. So that is how you find the equivalent resistance if it is not a balanced Wheatstone bridge. Okay. In our next problem, if we see, again it is not a balanced Wheatstone bridge because 1 into 4 is not equal to 2 into 3. That means we have to apply certain technique. First of all, finding equivalent resistance, you have to remove voltage source and current source. Now removing voltage source means we have to keep V equal to 0, that is short circuit. Removing current source means I equal to 0, that is open circuit. So here we will have to short circuit the voltage source like this. That means these 2 points are connected with each other. Now see these resistances 1 and the 3 ohm. They already had one node common. So this also becomes common. Okay. Now due to which these 2 resistances are coming in parallel. So let me call it as R1 their equivalent. In parallel, R1 will be 1 into 3 by 1 plus 3, that is 3 by 4 ohm. Similarly, 2 and 4 have two nodes in parallel. One is this, other is this by short circuiting. 2 into 4 by 2 plus 4, that is 8 by 6 or 4 by 3 ohm. Now both will be connected in series because it will be like this. 3 by 4, 4 by 3, and we have to find across this. So our equivalent will be 3 by 4 plus 4 by 3, that is 25 by 12 ohm. That is the equivalent resistance. In the next problem, if we see, here we have a current source. Okay. So to remove the current source, we have to remove current source. What we will do is, we will open circuit. How will the circuit look like? This. Like this. Okay, that is your 3 ohm. 1, 2, 3, 4. We have to determine across this. Now what will happen is, since they are not connected in parallel now, why? Because now the current source is opened and it is not shorted. Okay. So what we have to do is, we have to consider this 1 and 2 in series. Okay, these two will be in series and these two also in series. So it will be 3 ohm, then it will be 7 ohm, and we have to determine across this. Now how can I do this is, because here current is 0, so we can neglect this resistance. I told you, if we have a short circuit in parallel to a resistance, then neglect that. If we have open circuit in series with a resistance, then also neglect it, because current is 0, so the voltage drop across this resistance will be 0. Now this 3 and 7 are in parallel. 3 into 7 by 10, that is 2.1 ohm. That will be the equivalent resistance. So let me summarize what we have covered in this lecture. We first saw the series and parallel connection. Then we saw star delta transformation. Then we saw, after star delta, open circuit and short circuit. In open circuit and short circuit, we saw if resistance is connected and we short circuit this, this is neglected because current takes the path of minimum resistance. If it is a resistance with the open circuit, then also it is neglected. Then we saw finding R equivalent. Okay. So this is all from this lecture. In the next lecture, we'll see some problems based on the basic concepts that we have learned so far. Hi guys, what we have covered so far in network analysis is, we first looked at the basic terminologies that are used in network. Then we moved on to see some of the network elements like resistance, capacitance and inductance. Then we saw the power sources in a network like dependent and independent sources. And at last we saw the method of analysis like nodal and the mesh analysis, which is based upon Kirchhoff's law. So in this lecture, we will be solving some problems that have appeared in GATE examination from these topics. So let us get started. In our first problem, it is said that we need to have a direct current IT through the ideal inductor L. We need to find the nature of voltage source VT. Okay. Now, the direct current means that IT should be constant. What we need is IT is constant. Then at first it would seem that VT would be equal to L di by dt. Since IT is constant, it would be 0. That means there should be 0 voltage applied across the inductor.
but that is incorrect actually. Why it is incorrect? Because if you are not applying any voltage source, then how come the current is flowing in the inductor? What is exciting the inductor? If there is no source, what is providing the energy to the inductor? So what happens is, we know that IT is equal to 1 by L integral Vt dt. Now if you take Vt is equal to delta t, then IT would be equal to 1 by L, because integration of delta t would come out to be 1, which is constant. Okay, so that means the nature of voltage source must be impulse. It should provide the energy to the circuit suddenly, then the voltage should go to 0, so that same energy is kept inside the circuit. Energy does not change, and hence the current also does not change inside the circuit. That is the basic principle behind direct current flowing in the circuit. So do not commit this mistake and take the voltage to be 0. Voltage should have the impulse function. So let us move on to our next problem. In this circuit shown in the figure, we need to find the capacitance between B and Y. Now, to find the equivalent capacitance, first we need to understand the series and parallel combination. For series combination, C equivalent is C1 C2 by C1 plus C2. For parallel combination, C equivalent is C1 plus C2. And I told you, when we try to find the parallel combination, then there should be two common terminal between the devices. For series combination, there must be only one common terminal. Now see these two capacitors CC and CS. They have this Y terminal common, and this terminal is short circuited. So these are in parallel. Similarly, this CC and CS are also in parallel. B terminal is common, and this terminal is also common. So they will be added in parallel. So what will happen is, this is my B terminal, this is CC, B, Y. Now CC and CS are in parallel, so it will become CC plus CS. It will also become CC plus CS, like this. Now if you see these two capacitors CC plus CS, they have only one common terminal. So they are in series, and in series we will take C1 C2 by C1 plus C2. Now since these are both equal, then C equivalent will become C by 2. If both capacitors are equal, then it will become half. So it will be like this, CC. This will be CC plus CS by 2. This is B terminal, this is Y terminal. Now since these both are in parallel, so equivalent capacitance will be addition of the two. It will be CC plus CS by 2. So how much it will be? 3 CC by 2 plus CS by 2. This will be the equivalent capacitance between B and Y. So just you have to apply series and parallel combination, but at the same time you need to take care while identifying series and parallel whether there are two terminals in common or whether there is only one terminal in common between the two impedances or two capacitances. Moving on to our next problem. Here the waveform of the current passing through an inductor of resistance 1 ohm and inductance 2 ohm is shown. We need to find the energy absorbed by the inductor in first 4 seconds. So it is saying that there is inductance of resistance 1 ohm. Actually the practical model of inductor is like this. Every inductor is nothing but a coil. So coil will also have some resistance. So it is saying we need to find the energy absorbed by inductor in first 4 seconds. So there will be two components of energy here. One is the energy that is being dissipated in the resistor as heat energy, and other is the energy that is being absorbed or stored by the inductor. So we will find both the energies, and the total of energies will give me total energy absorbed by the inductor. So let us first find the energy stored in this inductance. Okay. So inductance has a voltage V is equal to L di by dt. So let us find the voltage across the inductor. Now if you see, this is the current. The slope of this current will be how much? This slope, it will be 6 by 2 is equal to 3 ampere per second. So the voltage would be L into 3. L is how much? 2. 2 into 3 is 6. 6 up to 2 second. Then since the current becomes constant, the derivative goes to 0. This will be the waveform of the voltage. Now power, I know power is equal to voltage into current. So if we do voltage into current, we know after 2 seconds the voltage goes to 0. So their product will also go to 0. So if we do voltage into current, what we will get is, we will get a waveform of something like this. After 2 seconds the product will go to 0, and at 2 seconds it will be 36. Because it is 6, it is also 6. So it will be 36. Now we know energy is equal to integral P dt, that is area under the power curve. So if you want to find the area of this triangle would be half into base into width, it is 36 joule. So 36 joule is the energy that is stored in the inductance. Now we need to find the energy that is being dissipated in the resistance. So we know the current waveform is something like this. The current waveform is like this. This is my 6 ampere. This is my 6 ampere. Okay. So power dissipated in the resistor is I square R. Okay. So this line would have an equation of 3t. At 2 seconds it is 6 ampere, and at 0 second it is 0. So to find the energy, we will take integral P dt. It will be integral 3t square into R dt from 0 to 2. But after 2 the current becomes constant at 6 ampere. So plus 6 square into R dt from 2 to 4 second. So it will be 9t square, 9t cube by 3, 0 to 2 plus 36 into t from 2 to 4. Okay. The resistance is how much? Resistance is 1 ohm. So I have removed the resistance from this expression. So how much will it come out? 3t cube into 8. So 3 into 8, 24 plus 72. It is 96 joule. So 96 joule is dissipated in the resistance. So total energy would be 96 plus 36, which is 132 joule. Okay. So 132 joule is the total energy absorbed by the inductor from the source, out of which 96 joule is being dissipated as heat and 36 joule is being stored as a stored energy in the electromagnetic form. Moving on to our next problem. Here we have been given a segment of the circuit in which VR is 5 volt, VC is 4 sine 2t. We need to find VL. So let us apply KCL at this node. Okay. So the current IR would be like this, IC would be like this, IL would be like this. IR, IC, IL. Now we know by KCL sum of incoming currents would be equal to sum of outgoing. So incoming current is 2 ampere and IR. 2 plus IR would be equal to IC plus IL. Both are outgoing current. So IL would be 2 plus IR minus IC. IR would be VR by R. And IC would be C dVc by dt. 2 plus 5 by 5 minus C is 1. dVc by dt would be 8 cos 2t. So it will be 3 minus 8 cos 2t. This will be my current through the inductor. But we need to find the voltage across the inductor. The expression for voltage across the inductor is VL is equal to L di by dt. Now I know the current. Let us take the derivative. 2 into d by dt of 3 minus 8 cos 2t. The derivative of 3 would go to 0 because it is constant. So it will be 2 into, it will be 16 sine 2t. So it will become 32 sine 2t. This will be the voltage across the inductor. So by KCL, first we find the current across the inductor and then we apply the expression VL is equal to L di by dt to find the voltage across the inductor. Let's move on to our next problem. In this figure given below, we need to find the value of resistance R. Okay. So here 8 ampere current is flowing. Let us assume there the current goes I1, I2. Now we saw in the current division that I1 would be equal to I R2 by R1 plus R2, that is 8 into 10 by 10 plus 10. It is 4 ampere. Similarly, I2 would also be 4 ampere. Okay. So 8 ampere current will be divided equally between these two resistances of 10 ohm. Since the resistances are equal, the current will also be divided equally between the two resistances. Now if we apply KVL like this, here the current 8 ampere is flowing, we will say 100 volt is equal to 8 into R. This is plus minus plus 10 into I1, that is 4. So 8 into R would be equal to 60, or R would be equal to 7.5 ohm. Okay. So this is how we apply the principle of current division. Whenever two resistances are connected in parallel, the total current is divided in these two resistances and it is divided based on this expression. This is my current division. In our next problem, it is shown in the figure that 1 ampere resistance is connected across the source that has load line V plus I equal to 100. Load line is nothing but, suppose we take VI curve, it is V plus I equal to 100. Okay. Now it is saying the current through the resistance. Now we know in a resistance V is equal to IR. So here resistance is of 1 ohm, so V is equal to I. And we know V plus I is equal to 100. So what I can say is 2I is equal to 100 or I is equal to 50 ampere. Actually, each circuit has its own load line, but due to resistance we have another line which is something like this. V is equal to I. The intersecting point gives me the operating point of the circuit. The intersection of these two lines which occurs at I is equal to 50 and V is equal to 50. That is my operating point of the circuit. This will make more sense when we will be studying analog circuits. There we will be taking the intersection of load line as well as the characteristics of the transistor to determine the operating point or the quiescent point of the amplifier or the transistor. Okay. So let us move on to our next problem. In the next problem, it is saying the current through the 2 kilo ohm resistance shown in the circuit. Now if you redraw this circuit, this is something like this. This is 2 kilo ohm, 1 kilo ohm, 1 kilo, 1 kilo. Now this is the classic example of a Wheatstone bridge. This is P, Q, R, S. Here if we see P by Q equal to 1, which is equal to R by S. This is called as balanced condition of the bridge. And whenever such a condition occurs, the current through this branch, I would be 0. Remember, whenever a Wheatstone bridge is balanced, there is no current flowing through this branch. Okay, the current through this branch is 0, as well as the potential difference between these 2 points would be 0, because potential difference would be IR. It would be 0. There is no current flowing through this resistance. This is the balanced condition of Wheatstone bridge, and you will learn more about it in the measurement course. In our next problem, it is saying two incandescent light bulbs of 40 watt and 60 watt rating are connected in series across the mains. Generally, whenever we buy a device, there are two ratings. One is the power rating like 40 watt, other is the voltage rating, let us say V volts. Now power in a resistance is nothing but V square by R. Okay. So resistance of any bulb would be V square by P. So resistance of 40 ohm would be V square by 40 watt, and resistance of 60 watt would be V square by 60. So from here what I can say is R40 is much greater than R60. Okay. Now when these two bulbs are connected in series, what happens? They will behave as resistance only. The thing is, the current through them will be same. When they are connected in series, the current will be same. So the power in 40 ohm would be I square R40, and power in 60 ohm would be I square R60. Now I know R40 is greater than R60. It would imply that P40 will be greater than P60. When they are connected in series, power dissipated in 40 watt bulb is more than 60 watt bulb. Okay, so 40 watt and 60 watt are just the rating of these bulbs. Do not confuse that the bulb will always consume this amount of energy. It just means it is the maximum amount of energy that can be consumed by the bulb. The actual energy will be lesser than this. So the 40 and 60 watt are just the ratings, but when they are connected in series, power consumed by 40 watt bulb will be higher as compared to 60 watt bulb. That means since it is consuming higher power, this bulb will glow brighter. Higher the power, higher will be the brightness of this bulb. That is what you might have seen in your homes also. Whenever the voltage drops, the intensity of the bulbs also goes down. And generally this happens when we switch to the inverter. Whenever the light goes off and inverter is functioning, the intensity of the devices drop down because the voltage supplied is not actually same as the mains voltage. It is a bit lesser than that. So the devices start consuming lesser power, and when they consume lesser power, then their intensity also goes down. That is, the fan speed will go down. The intensity of glowing of the bulb will also go down. Moving on to our next problem. It is required to find the value of current I when each resistance is 1 ohm. So now if you see, these two resistances are in parallel, one common terminal, second common terminal. Similarly, these two are in parallel, these two are in parallel, these two are also in parallel. So when 1 and 1 ohm are connected in parallel, the equivalent would be 1 into 1 divided by 1 plus 1, that is 0.5. Okay, when equal resistances are connected in parallel, their equivalent is half of that. R equivalent would be nothing but R by 2 when R and R are connected in parallel. So this circuit would become something like this. Okay, this will be 0.5, 0.5, 0.5, 0.5. This will be 1, 1, 1, 1. There will be one more resistance behind this. Okay. Now if you see, this 1 and 0.5 are in series. This 1 and 0.5 are in series. So it will become like this. 1, 1.5, 1.5. Okay. Now these 1.5 and 1.5 will be in parallel. Okay. So the equivalent resistance would be half of this. It would be 0.75. So it will be 1, then equivalent would be 0.75. Similarly, there will be one lower branch, 1.75. Okay, and 1 ohm is here, this one. Okay, now these two are in series, 1 and 0.75, it will be 1.75. This will also be 1.75. And then their equivalent would be in parallel. So this entire would become something like this. 1 ohm. Next would be 1.75 by 2. This will be 1.75, 1.75. Both are in parallel. 1.75 by 2. So R equivalent is 1.875 ohm. Now we know the total current would be V upon R, V by R, that is 1 upon 1.875. So it will be 0.533 ampere. This will be the current flowing in the circuit. So this is just a classic case of series and parallel combination of resistances, in which we need to find the equivalent resistance and then find the total current through the battery. Moving on to our next problem. In this circuit, it is saying all the resistances are in the figure are of R ohms. The switch is initially open. What happens to the lamp intensity when the switch is closed? So first of all, if you observe this circuit, this is R, this is R, this is R, this is also R. Okay. Now this is again an example of Wheatstone bridge. R upon R would be equal to R upon R, which is 1. So this resistance does not carry any current, hence this can be removed. So the only circuit that remains is like this. So initially when the switch is open, the battery is connected like this, R, R, R and R. Okay. Now these two resistances R and R are in series. Similarly, these two are also in series. So it will be 2R, then again 2R. So it will become R. When two equal resistances are connected in parallel, equivalent is half of those resistances. So when the switch is open, the equivalent resistance comes out to be R. Now next consider the case when the switch is closed. When the switch is closed, what happens is we are short circuiting these two. Now these two resistances R and this R, they have two common terminal, one this and one through the short circuiting. So they are in parallel. Similarly, these two resistances are also in parallel. So it will be, since when they equal resistances are in parallel, equivalent is half R by 2, R by 2.
Now these two are in series, so it will be R. So when the switch is closed, resistance is again R. So the equivalent resistance does not change even when the switch is closed. Since the equivalent resistance does not change, the current is constant, I will remain constant. Since I remains constant, the intensity of lamp will also remain same. So what happens to the lamp intensity? The lamp intensity remains the same because the circuit draws the same amount of current from the source. The current in the circuit does not change, and hence the lamp intensity remains the same. Moving on to our next problem. It is saying we need to find the value of E and I for this circuit. Okay. So since this 4 ohm and 1 ohm are connected in parallel, the voltage across both will be same. So 2 ampere is here. Voltage would be 2 into 4, 8 volt. Same voltage will be across 1 ohm. So current across 1 ohm would be 8 by 1 equal to 8 ampere. So 8 ampere would be going through here. Now by KCL, what I can say, 2 ampere is going here, 8 is going here. So 10 should be coming here, because sum of outgoing current should be equal to incoming current. Outgoing current is 10 ampere. Incoming should also be 10. Okay. Now this 6 ohm, if we apply KVL, suppose the current I is here. So voltage across 6 ohm would be 6I. This should be equal to this voltage across 1 ohm plus voltage across 4 ohm by KVL in this loop. So 6I should be equal to voltage across 1 ohm is 10 into 1 plus voltage across 4 ohm is 4 into 2. That is my 18. So I would be 3 ampere. So the current that is flowing in this resistance of 6 ohm is 3 ampere. So if we mark the currents now, here 8 ampere current, here 10 ampere current, here 3 ampere current. Again by KCL, what I can say, incoming current should be equal to outgoing. It should be 13 ampere. 13 ampere should be the incoming current. Now we apply KVL in this loop like this. So EMF would be equal to 13 into 1 plus 6 into 3. That is 13 plus 18, which is 31 volt. So current I comes out to be 13 ampere and EMF comes out to be 31 volt. That is, the battery EMF is 31 volt and the current that is supplied is 13 ampere. So it is just a basic KVL and a KCL problem. Now what you will observe in the GATE examination, most of the questions are like this only. They are based on very basic laws, that is KVL and KCL, or the nodal and mesh analysis. So that is why these concepts are of utmost importance to any student. The very basic question will be asked from network analysis. Moving on to the next problem. It is saying the circuit shown in the figure is equivalent to a load of. Here we see first time we are encountering a dependent source. So since I is coming here, some part will be going here, let us say I1, and I minus I1 will be going here. Now let us apply KVL in this loop. We will say I1 into 4, we are going like this, from minus to plus, minus 2 into I minus I1 minus 2I should be 0. So it will be 4I1 minus 2I plus 2I1 minus 2I should be 0. 6I1 is equal to 4I. So I1 equal to 2 by 3 I. Okay. So now if we calculate the voltage across these terminal, voltage would be I1 into 4, which is equal to 2 by 3 I into 4, which is 8 by 3 into I. So V by I would be 8 by 3 ohm. So this is equivalent to a load of 8 by 3 ohm. So what we can do is, it will be nothing but Here V voltage is applied, I current is flowing, it is 8 by 3 ohm. Okay, so I have done nothing but I have calculated the voltage across this parallel combination, then divided it by the current to find the equivalent impedance or equivalent resistance. So this circuit is nothing but it is similar to a resistance of value 8 by 3 ohms. Let us look at our next problem. It is saying that consider the star network shown in the figure. The resistance between A and B with C open. Now this C is open circuited. The resistance between A and B would be, if C is open, this resistance does not have any significance, no current flowing through it. The current resistance would be RA plus RB. This is given to be 6 ohm. Similarly, resistance between B and C with A open. If A is open, RA does not carry any current, we will say equivalent is RB plus RC. It is 11 ohm. The resistance between C and A with B open is RA plus RC. This is 9 ohm. Now if we add all these equations, we will get 2RA plus RB plus RC will be 26 ohm. So RA plus RB plus RC would be how much? 13 ohm. Now if you subtract first equation from this, 13 minus 6 would give you RC. RC would be 7 ohm. For that we need to subtract first equation from this RA plus RB plus RC. Then subtract second equation. What we will get is RA. RA would come out to be 2 ohm. Then subtract third equation from this. What we will get? RB. RB would be 4 ohm. So RA is 2 ohm, RB is 4 ohm and RC is 7 ohm. These are the three resistances that have been connected in the star network. In the next problem, we have been asked about the value of resistance R. Okay. So first let us see what kind of currents are flowing in the circuit. So let me assume that I1 current goes here. So the current coming here will be 10 minus I. I1 would be coming, let us assume this I only, 10 minus I. I current will be coming here. Current going here would be 5 plus I. 10 minus I is coming here, 5 plus I is coming here. Current going through here would be 15. 10 minus I plus 5 plus I. It will be 15 ampere. Now let us apply KVL in this loop. It will be 100 minus 14 into 10 minus I minus 2 into 15 equal to 0. So 100 minus 140 plus 14I minus 30 equal to 0. So I will be 5 ampere. That is 5 ampere current flows through this resistance R. Now what to do is, suppose this is my ground potential. So here the potential is 100 volt. Here the potential is 40 volt. So voltage across resistance R would be 100 minus 40, which is 60 volt. And I know the current is 5 ampere. So resistance R would be 60 by 5, that is 12 ohm. So here the resistance R connected between these two terminals comes out to be 12 ohm. So first I have applied the mesh analysis where I have applied KVL. Then we have taken the nodal analysis so as to find the resistance R. Otherwise you could do it with mesh analysis also, but the next step becomes a lot easier if you do nodal. So I have taken the mixture of nodal as well as mesh analysis to analyze this circuit quite easily. Otherwise you would have to apply KVL in one other loop to find the resistance R. In our next problem, it is saying RA, RB, RC are 20, 10 and 10. We need to find the R1, R2, R3. So we are doing delta to star conversion. Now R1 is connected between RB and RC. It will be RB, RC over RA plus RB plus RC.
So how much will it come out? 10 into 10 divided by 20 plus 10 plus 10. That is 100 by 40. It will be 2.5 ohm. Similarly, R2 is connected between, R2 will be here. It will be between RA and RC. RA RC over RA plus RB plus RC. So it is 20 into 10 divided by 20 plus 10 plus 10. So it will be 5 ohm. Similarly, between RB and RA, R3 is connected. RA RB over RA plus RB plus RC. It is 20 into 10 divided by 20 plus 10 plus 10, which is 5 ohm. Okay, so this is how we can find the resistances that should be connected in the star equivalent of the delta connection. So this is how we perform the delta to star conversion. Let's look at our next problem. It is saying in the circuit shown in the figure, we need to find the value of current I. Okay, and here we have a dependent source 4 times VAB. So let us assume this is the ground potential. This is VA, this is VB. Now in this loop, if we apply voltage division, VA would be 5 into 1 divided by 1 plus 1. It is 2.5 volt. So we know VA is 2.5 volt. Okay. Now let us apply KVL in this circuit also. In the second loop, 4 VAB minus 3I minus I equal to 0. So I would come out to be VAB. Now the potential across 1 ohm is VB. VB is equal to I into 1, which is equal to VAB. So VB is equal to VA minus VB. VAB is VA minus VB. So 2 VB is equal to VA, or VB is equal to VA by 2. Now VA is 2.5, so VB will be 1.25 volt. I know that VB is 1.25, VA is 2.5. VAB will be 2.5 minus 1.25, which is 1.25 volt. Now I know current I is equal to VAB. I would be 1.25 ampere. So this is how we analyze the circuit containing the dependent sources. Okay, they must be treated as a normal voltage source under all circumstances. Okay, unless we are talking about the superposition theorem, they must be treated as the normal voltage source. Moving on to our last problem in this session. Here we need to find the mesh analysis, and we need to find I1, I2 and I3. So let us mark the terminals like this: plus minus, plus minus, plus minus. Okay, applying KVL in this outer loop like this. So plus 12 minus 4, the current through 4 ohm would be I1 minus I2, minus 6, current through this would be I3 minus I2, minus 10 would be equal to 0. So it will be 4 I1, then minus 10 I2 plus 6 I3 would be equal to 2. This is my first equation. Okay, now let me remove this. If you see here now, the current in this branch is 2 ampere going upward. I3 is flowing like this, I1 is flowing like this. So 2 ampere would be I3 minus I1. This is my second equation. Next we apply KVL in the upper loop. So KVL in the upper loop will give me 4 into current through this 4 ohm is I1 minus I3 minus 2, sorry, I1 minus I2 minus 2 I2 plus 2 volt plus 6 I3 minus I2. This should be 0. So my third equation would be, what it will be? 4i1. Then what will be the degree of I2? Minus 10i2. Sorry, minus 12i2. Then plus 6i3. It should be equal to minus 2. This will be my third equation. Now we have three variables, I1, I2 and I3. We have three equations in I1, I2 and I3. Now you can plug this in your calculator to solve an equation of three variables. It will come out to be I1 would be 1 ampere, I2 would be 2 ampere, I3 would be 3 ampere. Now it is saying we also need to find the power developed in 10 volt source. Power is nothing but V into I. The current in 10 volt source is I3, that is going inside the positive terminal. So power between 10 volt is 10 into I3, that is 30 watt. But since current is going into the positive terminal, it is absorbing the power. Okay. When current comes out of the positive terminal, it delivers the power. When current goes into positive terminal, it absorbs the power. So here 10 volt voltage source absorbs the power and 12 volt voltage source will deliver the power. So these kind of questions can be asked from this network elements, basic network analysis, and mostly these kind of questions are commonly seen in the GATE examination. You can expect one or two questions of these type. Okay. In the next lecture, we will start with the network theorem and see how we can simplify the network analysis by the use of those theorems.
Hi guys, up to now we have seen just the basics of the network theory. That is, we have seen the network elements which are resistance, inductance and capacitance, and we have seen the connection of those elements, in which we have seen 3 or 4 types of connection like series and parallel connection and delta and star connection. And we have seen how to find out the equivalent of those connections. In this lecture, we will be studying some special concepts known as the network theorems. So what are the network theorems first of all? These are aimed at simplifying the analysis. There are certain set of rules which you follow while circuit analysis in order to make the analysis simple. Okay. Now, these are usually based on KVL and KCL. Okay. What all network theorems are present? First one is known as superposition theorem. Then the next one is known as Thevenin's theorem, Norton theorem, maximum power transfer theorem, Millman's theorem, and the last one is Taligin's theorem. So these are some theorems which are generally used in the circuit analysis, and the entire aim is to make the analysis simple. So let us start with our first theorem, that is my superposition theorem. So in superposition, as you can understand by the name superposition, we are basically superimposing multiple sources. Now actually, a single network may have multiple supplies, or it can have multiple energy sources. Like it can have, let us say, one current source, one voltage source. So in case of multiple sources, the total response is actually sum of the responses of all the sources. Okay. That means total response is equal to summation response due to each and every source, where n is the number of sources. That means suppose you want to find the current in certain element and the circuit consists of 5 sources. Then find out the current due to each source and then add those currents with the direction, because some sources may circulate the current clockwise, some may circulate anti-clockwise. Then you will get the total current through that element. Now this theorem is applicable to linear, active and bilateral elements. Okay, means you cannot apply it for the case of unilateral element like diode. Okay, because under different operating conditions, like when both the sources are operating simultaneously, it may so happen that diode may turn off. Okay, but when you operate individually, the diode may be on. So that is a problem issue. Okay, so we want the circuit should be bilateral before applying this theorem. Now how to apply superposition theorem? Like if you want to find out the output due to source 1, then short circuit all other independent voltage source. Okay, open circuit all other independent current source. Okay, leave dependent sources. Do not touch any dependent source. Leave them as it is. Okay, actually when we are trying to find the response, we are only dealing with independent sources. That means if I am saying that there are n sources, I mean to say there are n independent sources. Okay, so when we are trying to find the superposition of all the responses, then you have to consider the responses only due to the independent sources, because you will never consider only the dependent source. Why? A dependent source can only be energized by means of a independent source. Otherwise, without any independent source, a dependent source can never work. Is it fine? So if your circuit has 10 sources, out of which 5 are independent, then you have to find the 5 responses, one corresponding to each independent source, and then add those responses. Remember, this theorem is not applicable for unilateral element as well as non-linear element. Okay, if there is any non-linear resistance like a varistor or something, then its theorem cannot be applied. Is it fine? Secondly, it cannot be applied for any parameters like power, because power is proportional to V square. So linearity is lost. you can apply it to find out voltage and current, not power or energy. Is it fine? So it can be applied to active as well as passive, but not to unilateral and nonlinear networks. The next principle is known as homogeneity principle. What is meant by homogeneity? It is meant that if you multiply the input, like if the output for x1t is y1t, then the output for kx1t must be equal to ky1t. That is the principle of homogeneity. That if we scale the supply by a factor, then the response will also be scaled by the same factor. Like if you see in this example, I have shown when 9 ampere current is the input, then how will the current get divided? This is 9 ampere. This is actually 6 ohm. This is actually 9 ohm due to series connection. Now by current division, here the current will be 9 into 6 because we have to use other resistance. 6 plus 9. That is how much? 3.6 ampere. Here will be 5.4 ampere. That is 9 minus 3.6. That is how we have derived the currents. Now I have changed the supply to 3 ampere. That is, we have multiplied 9 into 1 by 3. That means this K factor is 1 by 3. So we have made the supply 1 by 3. Now if you see the response, this response 1.8, it is actually 5.4 by 3. 1.2, it is 3.6 by 3. Okay, that is response also becomes 1/3. It means the rule of current division does not change because the circuit parameters are still the same. Okay, like if the current was being divided in the ratio, what is the ratio here? 3:2. So it will still be divided in the ratio of 3:2, but the total current changes, so individual currents also change. But their ratio depends only on the circuit elements, hence the ratio is still constant. Because the ratio of the currents will be equal to R2 by R1, that is 9 by 6. This should be 3 by 2 irrespective of the supply. So it remains constant. Let us look at a problem on applying the superposition theorem. Now here as you can see we have two sources. One is the current source, other is a voltage source. We have to find the total current. So let us first find due to the current source. So we will short circuit voltage source. If we short circuit the voltage source, the circuit becomes like this. 1 ohm. This is 1 ohm. 1 ohm. 1 ohm. This will be short circuited. This will again be 1 ohm. Okay. Now since you have short circuited these two terminals, this resistance and this resistance have two nodes in common. One is this, other is this. So they will be connected in parallel. And these two resistances also have two nodes in common. One is this, other is this. So the equivalent of this 1 and 1 in parallel will be 0.5. Then there is a resistance of 1 ohm. Then this 1 and 1 in parallel will be 0.5. So this is how these resistances will be connected. Here we will have a current source. Now when the current is passing 1 ampere here, it will be divided into I1 and I2 here. So these 1 and 0.5 ohm are in series. So I can find out I1. It is 1 into 0.5 divided by 0.5 plus 1.5. That is 0.25 ampere. So actually I is equal to 0.25 plus X, where this X is the current component due to this 1 volt source. That means I know the response due to the current source. Now I want to find the response due to the voltage source. So now what we will do is, we will open circuit the current source and try to find the response due to voltage source. So if we open circuit the current source, what will happen is, this is 1 ohm resistor. 1 ohm. Like this. Here we have a voltage source plus minus. Here we have a resistance like this. Now this is typical configuration of a Wheatstone bridge. In a Wheatstone bridge, what happens is here we have a supply PQRS. If PS is equal to QR, then it is called as balance condition, and the current in this case is 0. Now if you see, supply is connected at the two terminals like this, and resistance is connected at the other two terminals like this. Here the product of opposite resistances 1 into 1 is equal to 1 into 1. So it is balanced Wheatstone bridge. Hence the current here I2 equal to 0. So what is the total current? I1 plus I2, that is 0.25 plus 0, which is equal to 0.25 ampere. Okay. So this Wheatstone bridge is very common in the gate examination. Also, you have to make a habit of identifying which circuit is working as a balanced Wheatstone bridge. The next theorem that we will study is the Thevenin theorem. Now, there are two theorems that are dual of each other, that is a Thevenin and a Norton theorem. In Thevenin's theorem, what we do is, to simplify the analysis, we will be having a network which will be linear. Okay, it will be consisting of resistances, inductances, capacitances, but it will be linear. And then this network will have certain supplies also, and it will be connected across a load, let us say RL. Now, what we want to do is to determine the solution of this network. The simplest kind of network would be what? A voltage source in series with a resistance, because then we know the current is V by R. So we want to convert this entire network into a voltage source in series with a resistance like this. Okay, these are the terminals. This is my load resistance. This is known as Thevenin resistance and Thevenin voltage. Now if you see, if you keep RL is equal to infinity or open circuit, then what is the output voltage here? VAB is equal to VThevenin. That is why it is also known as VOC, that is the open circuit voltage. So essentially what I am doing is, I am converting a linear network consisting of resistances, inductances and capacitances into a open circuit voltage in series with a Thevenin resistance, or even you can call Thevenin impedance. But this concept of Thevenin impedance will be used when we will be studying the AC circuits. Right now we are studying DC circuits, so I'll directly use the Thevenin resistance. Is it fine? So now the analysis of the circuit is simplified because I know the load current will be VThevenin by RThevenin plus RL. Okay, this way we can calculate the current as well as power and efficiency also. Similarly, the Norton's theorem is there to simplify a linear network consisting of R, L and C. So again, if I am given a linear network, this time I will not convert it into a voltage source because the other representation can be a current source. So here I will convert it to a current source in parallel to a resistance. Okay, like this. Now this is the Norton's current, this is Norton's resistance. Now actually we can obtain Thevenin and the Norton equivalent from one another. How? What is the Thevenin equivalent? VOC. Then RThevenin, like this. If you convert this voltage source to a current source, how it will be? VOC by RThevenin, and then this will be RThevenin. That means if we compare it, RThevenin is actually same as
R Norton. So Thevenin and the Norton resistances are equal. What about I Norton? I Norton is equal to VOC by R Thevenin. Now suppose we short circuit these terminal. Then this entire current always tries to take the path of minimum resistance. It will go like this. That is why Norton's current is also known as short circuit current. So one method of finding R Thevenin is VOC by ISC. Okay. That is, determine the open circuit voltage and the short circuit current, and their ratio will give me the Thevenin or the Norton resistance. Okay. Now, we will apply these theorems when we want to find R Thevenin. Then what you will do? You will remove all the independent voltage sources, because Thevenin resistance is nothing but equivalent resistance across the output terminals. Okay. So when we want to apply this, so actually Thevenin resistance is nothing but it is equivalent resistance across A and B. So you have to keep certain points in mind while applying the Thevenin and the Norton theorem. First of all, while finding R Thevenin, short circuit independent voltage source. Okay. Open circuit independent current source. That is, we have to remove all the independent sources. Okay. Do not touch dependent sources. You don't have to do anything to any dependent source. They will remain in the circuit as it is. Okay. Then these theorems are applicable to all sort of circuit. Okay, no matter what type of circuit is there, Thevenin and the Norton theorem can be applied to any circuit. It does not depend on type of element. Okay, it does not depend on type of voltage and current sources. Whether the sources are dependent, independent, it does not depend on that. It can be applied. But it cannot be again applied for non-linear and unilateral elements. That means the linearity and the bilateral elements are necessary. It cannot be applied to non-linear elements. Is it fine? And as we know, you can apply one theorem and then you can find the other equivalent directly by using the source transformation technique. Now let me show you how to find out the Thevenin or the Norton's equivalent under different type of sources. So first let us take the example when there are only independent sources in the circuit. There are no dependent sources. So let me first work with the Thevenin equivalent. To find out Thevenin equivalent, we have to find open circuit voltage. Now as response is shown across this resistance, we have to open circuit this resistance. So we have open circuited this. Then this 2 ampere current source is connected in series with these resistances. That means here 2 ampere current will flow. So positive negative will be like this. This is 10 volt. Now what is VAB? It is 10 plus V 1 ohm. What is V 1 ohm? 1 into 2 ampere, that is equal to 12 volt. So this is the open circuit voltage, or we can say Thevenin voltage is 12 volt. Now if you want to find out Thevenin resistance, you have to short circuit all the independent voltage sources and open circuit the current sources. So we have open circuited this and we have short circuited this. Now if you see the resistance across A and B, the resistance across A and B is actually 1 ohm. So that will be your Thevenin or the Norton resistance. So how we will draw the Thevenin's equivalent? We will draw Thevenin equivalent like this. 12 volt, then 1 ohm Then here there will be a load of 2 ohm. Then what will be the current here? 12 by 3, that is 4 ampere. Okay. So this will be the current through the resistance that is found out by using the Thevenin's equivalent. Now let me show you how to apply the Norton's equivalent. To find out Norton's equivalent, we have to find the short circuit current. To find out short circuit current, we will short circuit this load. That means 10 volt, 1 ohm, then short circuit this load, 3 ohm and 2 ampere. Now, if we apply KVL, I can find out this current I1. I1 will be 10 by 1, which is equal to 10 ampere. And this 2 ampere current will also flow like this. So the total current I will be 10 plus 2, that is 12 ampere. Okay. That means the short circuit current or the Norton's current, this is equal to 12 ampere. Is it fine? Now we need to find the Norton's resistance. As I told you, Norton resistance is nothing but the Thevenin resistance, which is 1 ohm. So how we will draw the Norton's equivalent? 12 ampere, then 1 ohm, then here we will connect the load of 2 ohm. To find out the current I here, I will apply current division. 12 into 1 over 2 plus 1, that is 4 ampere. The same result that we got from the Thevenin's theorem. And you can see here also, this current source is nothing but Thevenin's voltage divided by the Thevenin resistance. So they can be obtained from each other by source transformation. I Norton is V Thevenin by R Thevenin. Okay. Next case is when we have independent as well as the dependent sources. Here also we need to find the Thevenin's and the Norton's equivalent. So first let us work with Thevenin. To find out Thevenin equivalent, we will open circuit the load. This is the load in this case. So this is plus minus Vx, 10 volt, 2 Vx, then this is 2 ohm. Okay. Now if you see here the current will be 0. So this 2 Vx current will go like this. Okay. Now the voltage across this 1 ohm will be, it is like 2 Vx into 1. But as per the current direction, the voltage should be like this. That is, this should be equal to minus Vx because the given voltage is like this. And but due to current, the polarity is opposite. That means 3 Vx equal to 0, or we can say Vx equal to 0. From this I get Vx equal to 0. If Vx equal to 0, then what is the open circuit voltage? It is actually equal to 10 volt. Okay. Because if you see here, the voltage at this point will be, let us say V1, 10 minus Vx, which is equal to 10. And since current is 0 here the voltage is 0 volt. That means open circuit voltage will be same as the supply, that is 10 volt. Next we need to find the Thevenin's resistance. But Thevenin's resistance we cannot directly calculate because we have a dependent source here. So what we do is, we calculate it other way around, that is R Thevenin is VOC by ISC. So let us calculate the short circuit current. So if you wish to calculate the short circuit current, then we have to first of all short circuit the load terminals. That is plus minus 10 volt, 1 ohm, 2 Vx, 2 ohm,
Then we will short circuit these terminals. Now once we have short circuited these terminals, this voltage is given to me as Vx. Based on this voltage, I can say that current flowing here will be Vx by 1, that is Vx. So by KCL, I can say the current going here is 3Vx. Now apply KVL. 10 minus Vx minus 2 into 3Vx must be 0. So 10 is equal to actually 7Vx, that is Vx is equal to 10 by 7. Then what is the short circuit current here? ISC is equal to 3 into 10 by 7, that is 30 by 7 ampere. What is the Thevenin's resistance? VOC by ISC, that is 10 divided by 30 upon 7, which is equal to 7 by 3 ohm. So that is how you can calculate the Thevenin's resistance as well as the Norton's current or the short circuit current. Is it fine? Then you can draw the Thevenin's equivalent directly. Open circuit voltage is 10 volt. Thevenin's resistance is 7 by 3 ohms. And then the load resistance, which is 3 ohm. So now I know the current. It will be 10 upon 7 by 3 plus 3. That is 16 by 3, so 30 by 16. Okay, or we can say 15 by 8 ampere. So that will be the load current by using the Thevenin's theorem. As you can see, this analysis is a bit more simpler as compared to applying KVL and KCL. Okay. Similarly, we can draw the Norton's equivalent. In Norton's, what was the short circuit current that I was getting? The short circuit current was equal to 30 by 7 ampere. Okay. And then there will be a Norton's resistance, which is equal to Thevenin's resistance, which is actually equal to 7 by 3 ohm. And then there will be a load resistance, that is 3 ohm. Now I can apply current division. 30 by 7 into 7 by 3 divided by 7 by 3 plus 3. So that is 10. 10 by 16 upon 3. So 30 by 16. That is 15 by 8 ampere. So this method also you can apply. Usually the more commonly used method or most commonly asked is the Thevenin's network. The last case is when we only have the dependent sources. Now as you can imagine, if you only have dependent sources, is that this circuit cannot function on its own. Because dependent sources depend on the independent sources. If there are no independent sources, the circuit has no supply. The circuit is unenergized. Okay. If circuit is unenergized, that means there can be no open circuit voltage. Is it fine? If there is no open circuit voltage, then we just have to find out R Thevenin or R Norton. We cannot find ISC or VOC. This cannot be identified. This will be taken as 0. So let us try to find the resistance across X and Y. Now since I told you dependent sources cannot work on their own, we have to give some supply. So let me assume I give a 1 volt supply here. I am assuming it gives a current I. Current I is coming here. 2V0 is coming here. So here it will be I plus 2V0. Okay. Now current in 2 ohm resistor is I plus 2V0. So V0, the voltage across the 2 ohm will be I2 into 2. That is V0 is equal to I plus 2V0 multiplied by 2. That is V0 is equal to 2I plus 4V0. So 2I is equal to minus 3V0, or we can say V0 is equal to minus 2I by 3. Now if we apply KVL along this loop, this 1 volt is equal to 4I plus I plus 2V0 1 plus V naught. 4i plus I, 2V naught will be equal to minus 4i by 3 minus 2i by 3. That is 5i minus, it will be 2i, that is equal to 3i. So what is the Thevenin's resistance? It is voltage source upon the current that is supplied. Okay, that is equal to 1 by V is equal to 1 is equal to 3i. So 3i by I, that is equal to 3 ohms. Okay. So the Thevenin's resistance is actually equal to the voltage that we have applied divided by the current that is supplied by this voltage source. So it is equal to 3 ohm. So these are the three cases where you have to apply the Thevenin's theorem. So let me summarize what we have covered in this lecture. We first saw superposition theorem, where multiple voltage sources or multiple sources can be dealt with by dealing only one source at a time. Though this theorem may not appear very important in the DC circuits, it is pretty much important when it comes to AC circuit. Why? Because in AC circuits, there can be multiple frequencies, so the circuit configuration will change at different frequencies. We have to apply superposition theorem in every case. Okay. Then we studied the homogeneity principle, in which we scaled the excitation and the output was scaled by the same amount. Okay. Then we studied the Thevenin's theorem, where we represented a linear network by the voltage source in series with a resistance. And we studied the Norton's theorem, where we replaced the entire network by a current source in parallel to a resistance. Then we studied three cases in which there were only independent sources. There were only dependent sources. There were both type of sources. So this Thevenin's and the Norton's theorems are very important as per the GATE perspective. So try to practice problems based on all the three cases. Is it fine? So this is all from this lecture. In the next lecture, we will see some problems based on this Thevenin's theorem. Hi guys, in our last lecture what we covered was, we took a look at the superposition theorem, homogeneity principle, as well as the Thevenin's and the Norton's theorem. I explained to you the various cases of the Thevenin's theorem in which there are only independent sources, independent as well as dependent sources, and at last only the dependent sources. So in this lecture I'll give you a look at how the problems are tackled when it comes to superposition as well as Thevenin and Norton theorem. So let us first get started with our first problem. It is saying the network is linear, containing only resistors. If the network is linear, it means superposition theorem can be applied. So let me say that the output is a linear combination of the inputs. That is, Vx let us say is I1 R1 plus I2 R2. That is what is meant by linearity. Now, in our first, where this R1 and R2 are here are proportionality constants and these are unknown. So let us find out R1 and R2 using the conditions given. If we use first condition, it is saying Vx will be 80 if I1 is 8 and I2 is 12. So this is our first equation. By second equation, it is saying Vx is 0 if I1 is minus 8 and I2 is 4. Now, if we add both these equations, this R1 term will get cancelled out. 16 R2 is equal to 80, which implies R2 will come out to be 5 ohm. Okay. That means 80 is equal to 8 R1 plus 60 from first equation. I have substituted the value of R2. That means 8 R1 will be 20 and R1 will come out to be 2.5 ohm. Okay. Now that we have the proportionality constants, we can find out the unknown output using the conditions given. Now I'll directly substitute the values. I'll say 2.5 I1 plus 5 I2. I1 is given to me as 20. I2 is also given to me as 20. That is 20 into 7.5, which will come out to be 150 volt. Okay. So in these sort of problems, you have to apply the superposition theorem to determine the proportionality constant for each source. Remember, whenever the network is consisting of the resistor, inductor and capacitor, it will be a linear network and you can apply these sort of concepts. Next problem is based on your Thevenin's and the Norton's theorem. It is asking VOC, R Thevenin, ISC, R Thevenin. That is, we have to draw the Thevenin equivalent as well as the Norton's equivalent. Now in this network, if you take a close look, this is a dependent voltage source, dependent current source. I told you whenever a voltage and a current source are connected in parallel, it can be replaced by a current source. That means I can redraw this network as like this. V2 by 5K, then this current source can be separated from this. Okay. 20K plus minus V2. Is it fine? So that way we can simplify this network to some extent by separating the voltage and the current sources. Next, what we do is, we first need to find the open circuit voltage. So let us first apply KVL in the first loop. Let me call the current as I1. Okay. So it will be 2 into 10 raised power minus 3, 2 millivolt minus 2000 I1 is equal to V2 by 5000. Okay. And KVL in the second loop will give me 50 I1 into 20,000 is equal to minus V2, because this current will go like this. So plus minus will be like this. That means V2 can be substituted as minus 50 into 20,000 I1. So if we substitute it here, or let us substitute better I1, because I need to calculate V2 na. So let us substitute I1. I1 will be minus V2 by 20,000 into 50 is 10 lakh, that is 10 raised power 6. Okay. That means 2 into 10 raised power minus 3 plus 2 into 10 raised power 3 V2 by 10 raised power 6 is equal to V2 by 5000. Okay. Now if I simplify this, collecting V2 terms on one side, 2 into 10 raised power minus 3, this will be V2 by 500 plus V2 by 5000. So here what I can do is, I can take out this V2 by 5000 common, minus 10 plus 1, that is minus 9. So V2 will be 5000 into 2 into 10 raised power minus 3 by 9. So it will come out to be minus 10 by 9 volt. So that will be my open circuit voltage, that is minus 10 by 9 volt. Now we want to find out the short circuit current. To determine the short circuit current, we will short circuit these terminals. If we short circuit these terminals, that means V2 goes to 0. If V2 goes to 0, then this source also goes to 0. So we can redraw the circuit like this. This is shorted here. And since we are shorting these terminals A and B, this 20K resistance has no significance. It can be short circuited. Okay. So if we calculate first I1, I1 will be 2 millivolt by 2K, that is 1 microampere. So the short circuit current ISC will be minus 50 I1, just applying KCL here. So it will be minus 50 microampere. Okay. Now how to calculate RThevenin? RThevenin is simply VOC by ISC minus 10 by 9 minus 50 microampere. Minus minus will get cancelled out. This will get cancelled out. That is 1 by 45 into 10 raised to power 6. That is actually 200 by 9 kilo ohm. So that is how we can determine the RThevenin. Okay. Otherwise, you can also determine RThevenin by applying a source at the AB terminals, because this circuit has independent as well as dependent sources. So to determine RThevenin, what we will do is, we will remove all the independent sources. So we will short circuit this. So this will remain 2K, current I1. Then if we apply a 1 volt source at V2, then V2 will be 1. So it will be 1 by 5000. Then this will be 50 I1 then this is 20K resistance. Here we have 1 volt voltage source. Let us say delivers a current I. So what will be the current going into the 20 kilo ohm resistance? It will be I minus 50 I1. Now to determine this I1, we can apply KVL in this loop. I1 will be minus 1 by 5000 divided by 2000. That is 1 by 10 raised to power 7. That is 0.1 microampere. Now that means current in the 20 kilo ohm resistor will be I plus 50 into 0.1 microampere. This will be the current in this resistance. Now what you need to do is, we know the voltage across this 20 kilo resistor, it is 1 volt. So it will be 1 by 20K I plus 5 microampere. 20K is actually 0.02 mega ohm. That is equal to 50 microampere equal to I plus 5 microampere. So I will come out to be 45 microampere. Okay. Now if you want to find out R, we will say it will be equal to voltage source that we have applied 1 volt by 45 microampere. that is 10 raised power 6 by 45, or it is 200 by 9k. Okay, that is how you can determine the Thevenin resistance. Moving on to next problem, it is again asking us to find the R Thevenin, R Norton, VOC, ISC. First of all, R Thevenin and R Norton are one and the same thing. Now if you see the network graph, if you see this point 20, when I is equal to 0, V is equal to 20 volt. I is equal to 0 means open circuit. If it is open circuit, that means VOC is equal to 20 volt. Now look at this point. If we see, when V is equal to 0, I is equal to minus 4 ampere. Minus 4 ampere means the direction of current will be reversed. It will be like this. If we short circuit this terminal, current will go into the short circuit. So I can say the short circuit current is actually 4 ampere. Then we know R Thevenin is equal to R Norton is equal to VOC by ISC, that is 20 by 4, which comes out to be 5 ohm. Okay, that way you can calculate the Thevenin and the Norton's equivalent. So how to draw Thevenin equivalent? It will be 20 volt in series with 5 ohm, and Norton equivalent will be 4 ampere in parallel with 5 ohm. These two networks can also be obtained from each other just by source transformation technique. In next problem, it is asking for the Thevenin resistance across A and B in the figure shown below. Now here again we have dependent as well as independent sources. So it is better that we apply a voltage source at AB and removing all independent sources. So first you have to remove independent sources. If you remove independent sources, this circuit will become this is actually 1K, current I, current here 99I, and here we will have a voltage source 1 volt, which let us say supply the current capital I. Now here if you see, I plus 99I plus capital I, this must be 0. That means capital I is equal to minus 100I. Now this, how to calculate this I? We know the voltage across 1 kilo ohm resistor is 1 volt. So I will be 1 volt by 1 kilo ohm with a minus sign. Because if plus minus are like this, then current should flow like this. In a resistor, current always goes from higher potential to lower potential, that is minus 0.1 milliampere. Then I can calculate I. Minus 100 into minus 0.1, that is minus 10. Sorry, it will be 10 milliampere. That means I can calculate R Thevenin 1 volt by 10 milliampere. It will come out to be 100 ohm. So that will be your Thevenin resistance. Now we know the voltage drop across the 1 kilo ohm resistor. It is 1 volt because this 1 volt voltage source and resistor are in parallel. That means I can be written as minus 1 by 1 kilo ohm. Why minus sign? Because here the plus minus terminals are like this. So current should flow like this. Okay, from a higher potential to a lower potential. So it comes out to be minus 1 milliampere. So this will be, I will be 100 times this, 0.1 ampere. Then if I want to find out V by I, that is 1 by 0.1 milliampere, 1 ampere, it will be 10 ohm. Okay,
That is, your Thevenin's resistance comes out to be 10 ohm. In next problem, it is asking for Thevenin resistance across 1 and 2 terminal. So let me redraw this circuit because I'll have to apply a voltage source here. This is a circuit consisting of only dependent sources. So if you see this 100 ohm resistor, it is connected between 1 and 2. So let me first draw this 100 ohm resistor. Then this 1K and 9K are in series and they are also connected across 1 and 2. So it is 10K. Current is flowing like this, IB. Then if you see this current source, it is injecting current into one terminal and it is also connected between 1 and 2. It will be like this. Now these are 1 and 2 terminals. Here we will apply a external or an independent voltage source, let us say 1 volt. Now it will inject some current I. Okay. Now this 1 volt is in parallel with 10K. So I can determine IB. IB will be minus 1 by 10K. That is minus 0.1 milliampere. Is it fine? Again, why minus sign? Because the current actually exists in the reverse direction. Now, since the voltage across this is same, what is the current in 100 ohm resistor? It is 1 by 100. That is equal to 10 milliampere. Okay. So if I want to find out I can say I plus 99 IB will be equal to 10 milliampere plus 0.1 milliampere. Okay, because this current is here 0.1 milliampere. Now, we know that IB is equal to minus 0.1 milliampere. I minus 99 into 0.1 is equal to 10.1. So I is equal to 10.1 plus 9.9, that is 20 milliampere. So R Thevenin will be equal to 1 upon 20 into 10 raised power minus 3. So it will come out to be 50 ohm. Okay. So that is your Thevenin's resistance, which is 50 ohms. In next problem, it is asking for Ix using the Norton's theorem. If I want to find out Ix, that is the current in the 2 ohm resistor using Norton's, then we have to find out the Norton's equivalent about this resistance. Now, if there is dependent as well as independent sources, then finding out the Norton's theorem involves two things: finding out the Norton's current and the Norton's resistance. Norton's resistance can be determined as VOC by ISC. So let us first determine open circuit voltage. So I will open circuit these terminals. It is 10 volt, 3 ampere. This means Ix has been reduced to 0. Here there is no current flowing in the 2 ohm. So if Ix has been reduced to 0, then this voltage source also gets short circuited. That means this 3 ampere current goes here. And this is 10 volt. So what is the voltage across 1 ohm? 3 into 1, that is 3 volt. So potential of this point is 3 volt. So that means, what is the open circuit voltage? It is 10 minus 3, that is 7 volt. Next thing we need to find out is the short circuit current. So I'll write it down here. VOC comes out to be 7 volt. If you want to determine the short circuit current, we will short circuit the term resistance 2 ohm. If we short circuit this resistance, it will become like this. Then 3 ampere
then 1 ohm, and here whatever is the current I, here it will be 2I. Then how to determine the short circuit current? We will say that here the current will be I plus 3, that 10 minus I plus 3 into 1 will give me 2I. That is 10 minus 3 will give me 3I, or I will be equal to 7 by 3 ampere. This is the short circuit current I. So ISC is 7 by 3 ampere. Then what is the Norton's resistance? 7 divided by 7 by 3, it will come out to be 3 ohm. Now let us draw the Norton's equivalent. The Norton's equivalent will consist of a current source of voltage, current 7 by 3 ampere. Then a Norton's resistance 3 ohm. Then a load resistance 2 ohm. So we have to find out the current in this 2 ohm. Now we can apply current division. 7 by 3 into 3 by 3 plus 2. That will come out to be 7 by 5, or 1.4 ampere. Okay. So that is the current in the 2 ohm resistor. Moving on to the next problem. It is asking the Norton's equivalent, that is the Norton current and the Norton's resistance. Now by first method, first I am trying to apply a superposition theorem here. Okay, since there are multiple sources, so what to do is, this is a 6 volt source. First we will short circuit this. First I will only use 6 volt source. So forget about this current source. Now there are two 3 ohm resistors in parallel. What will be the R equivalent for these two resistances? 3 into 3 by 3 plus 3, that will come out to be 1.5 ohm. Okay. Then what is R overall? 3 plus 1.5, that is 4.5 ohm. Then what is the current from this voltage source? It will be 6 by 4.5, that is equal to how much? 6 by 4.5, it will be 4 by 3 ampere. Okay. So this will be the current. That means what is the current in this short circuit? It will be the same current that flows in this resistor. So now we will apply the current division. 4 by 3 into 3 by 6. That will come out to be 2 by 3 ampere. So the first short circuit current is 2 by 3. Next, let us use the current source. If we use only the current source and short circuit this voltage source, we will get a circuit like this. These are two 3 ohm resistors. Then this is my current source. This is the other resistor. Now these 3 ohm resistors are actually becoming 1.5 ohm. So I can modify this circuit as like this. (1.5 ohm). So this is the 2 ampere current source. So whatever is the current in this 1.5 ohm will be traveling like this. That means I short circuit 2 is actually the current in 1.5 ohm. So we can apply current division. It will be 2 into 3 by 4.5. That is 4 by 3 ampere. Then what is the overall short circuit current? 2 by 3 plus 4 by 3, that is 2 ampere. Now since this is a circuit consisting of only independent sources, we can directly determine the Norton's resistance. We will short circuit the voltage source. and we will open circuit the current source. So it will be 3 in parallel with 3 is 1.5. So it will be 3 plus 1.5, that is 4.5 ohm. So that is one of the methods to determine the Norton's current and the Norton's resistance. Other method could be a lot simpler than this. First, what I will do is, I will convert this half of the circuit into Thevenin. That means if I draw this circuit again, 6 volt, 3 ohm, 3 ohm. Then what is the open circuit voltage? 6 into 3 by 6, that is 3 volt. And what is the Thevenin resistance? That will be 3 in parallel with 3, that is 1.5 ohm. Okay, when we short circuit this 6 volt, they will be in parallel. Now this circuit can be redrawn as 3 volt, then 1.5 ohm, then transform this current source into voltage source. It will be 2 into 3, 6 volt, 3 ohm. Okay. Now we will short circuit these terminal. If we apply KVL now, 3 plus 6 is equal to 4.5 I. So I will come out to be 2 ampere. Okay. So that is how we can easily determine the Norton's current using the Thevenin's theorem. In our last problem, it is asking the Thevenin equivalent across the terminals A and B. Now to determine Thevenin's equivalent, we have to find out open circuit voltage and Thevenin resistance. Again using the same method, first I will find out Thevenin equivalent of this section. So if I find out the Thevenin's equivalent of this section, I will redraw this circuit again. 5 volt. This is 2K. 2K. So what is the open circuit voltage? 5 into 2 by 4, that is 2.5 volt. What is the Thevenin's resistance? 2K in parallel with 2K, that is 1 kilo ohm. Okay. So now what to do is, I will redraw this circuit. 2.5 volt, 1 kilo ohm resistor, then it is 3 VAB, then again 1 kilo ohm resistor, and this will be VAB. Okay. So this is a new transformed circuit. Now if you want to determine the open circuit voltage, if you want to determine open circuit voltage, applying KVL here, assuming a current I, 2.5 minus 1 into I minus 3 VAB will come out to be VAB. Okay. That means 2.5 minus I is actually 4 VAB. But if we see across this resistance, current is I, resistance is 1, and the voltage is VAB. That is I is equal to VAB. So 2.5 is equal to actually 5 VAB, or VAB is equal to 0.5 volt. Now we need to determine the Thevenin resistance. And since this is a circuit consisting of independent and dependent sources, we have to do either two things. Either you can find out short circuit current, or you can apply an external source at AB terminals. So let us first short circuit this terminal. If you short circuit this terminal, this voltage source goes to 0, as VAB is 0. This resistance can also be removed. So what will happen to this circuit? It will become something like this. 2.5 volt, 1 kilo ohm, then it will be short circuit. Then what is ISC? 2.5 milliampere. So what is Thevenin resistance? It will be 0.5 volt by 2.5, that is equal to 200 ohm. So this way it is much more simpler to determine the Thevenin resistance if we just apply the VOC upon ISC. Okay. Otherwise the other method could be to apply a external voltage source at AB terminals. So these sort of simple problems are asked on the Thevenin's and the Norton's theorem. Just need to remember the basics, that is the three cases that we did: dependent and independent sources, and independent sources, and only the dependent sources. Okay. So this is all from this lecture. Hi guys, in the last lecture we completed the study of network theorems. We saw Millman's theorem, we saw Telegan's theorem, maximum power transfer theorem, and other theorems that we covered earlier were Norton's and the Thevenin's theorem and the superposition theorem. So these are some of the theorems that are very helpful in simplifying the network analysis, and so that we can derive certain parameter or the response of a network. In this lecture what we'll do is we'll see some of the previous year problems from the network theorems to gain a better understanding on how to apply them when it comes to actual networks. So let us get started with our first problem. It is asking, in the circuit shown, find the value of load resistance for maximum power transfer. Hence calculate maximum power transfer to the load. Now actually we haven't covered two-port parameters, but these are given as Y parameters. So in terms of Y parameters, what I can write down, I1 is equal to 5V1 plus 4V2. Similarly, I2 is equal to 4v1 plus 5v2. Okay, based on this matrix. Now, to calculate the maximum power transferred, we need the Thevenin equivalent. And for Thevenin equivalent, we need open circuit voltage and R Thevenin. So let us first find out open circuit voltage. For open circuit, what will happen is I2 will be 0 and V2 will be written as VOC. Then I can write down I1 is equal to 5V1 plus 4VOC and 0 is equal to 4V1 plus 5VOC. Other equation I can frame by KVL here. I can write down 100 is equal to I1 plus V1. Okay. Now if I simplify this equation, from this equation I can determine V1 in terms of VOC. I can write down VOC is equal to how much? Minus 4 by 5 V1. Then I can substitute in this equation. I1 is equal to 5 V1 minus 16 by 5 V1. That is actually equal to 9 by 5 V1. And I know I1 plus V1 is 100. So I1 plus V1 is 100, where I1 is 9 by 5 V1. It is 100. So 14 by 5 V1 is 100. So how much will V1 come out to be? V1 will come out to be, this is 7, this is 50. So V1 will be 250 by 7 volt. What about I1? I1 will be 450 by 7 ampere. Now I know I1 and V1. I can calculate VOC. VOC was how much? If you see, VOC was minus 4 by 5 V1. So that is minus 4 by 5, 250 by 7. It implies minus 200 by 7 volt. Now that I know Thevenin voltage, I need to calculate the Thevenin resistance. Thevenin resistance can be calculated VOC by ISC. So to calculate short circuit current, we will equate V2 equal to 0. When you short circuit the load terminals, V2 will be 0 and I2 will be written as minus ISC, because the short circuit current must go into the load. So do remember this thing. In actually two-port parameters, what we do is we show the current entering from both the ports or from both the terminals. Whereas whenever we will short circuit the load terminals, the current should go into the load or it should come out of the network. That is why I2 is equal to minus ISC. And if we substitute in this equation, in the Y parameter equation, then what will happen is minus ISC is equal to, what were the Y parameter? 4 and 5? 4V1 plus 5 into 0. And I1 is equal to 5V1 plus 4 into 0. This was my I1. Now I know I1 plus V1 is also 100. From here I can calculate the relation between I1 and V1. I1 is equal to actually 5V1. So 6V1 is 100, which implies V1 is 100 by 6. Now that I know V1, I can calculate ISC. How much is the ISC? It is 4 into 100 by 6. That is minus 200 by 3 ampere. Now that I know VOC as well as ISC, I can calculate Thevenin resistance. What will be Thevenin resistance? It will be minus 200 by 7 divided by minus 200 by 3. That is equal to 3 by 7 ohms. Now to calculate maximum power transferred into the load, what we will do is, it will be open circuit voltage square by 4 R Thevenin, that is 200 by 7 whole square by 4 into 3 by 7, which comes out to be 476.19 watt. That will be the maximum power transferred, and the load resistance must be equal to Thevenin, that is 3 by 7 ohms. Okay. So sometimes even you have to derive the Thevenin's parameter from a two-port network. You will have to play with the equations in order to determine the Thevenin parameter. Let us look at next question. Here it is saying with 10 volt DC connected at port A. Okay. In the linear non-reciprocal two-port network shown in the below, the following were observed. Okay. The first statement is 1 ohm connected at port B draws a current of 3 ampere. So what I'll do is, I will assume a Thevenin equivalent across port B. I am assuming. Now it is saying 1 ohm connected at port B draws a current of 3 ampere. By KVL what I can say is V Thevenin is equal to I into R Thevenin plus I load, R load, where I is the current flowing through the load. So if we go by first statement, I'll say that V Thevenin is equal to current is 3 ampere into R Thevenin plus 1. And by the second statement, what I can say? V Thevenin is equal to 2 ampere into R Thevenin plus 2.5. Now if we solve these two equations, what I'll get is, I'll get that R Thevenin is 2 ohms and V Thevenin will come out to be 9 volt. Actually for both the equations, how I am assuming that the V Thevenin remains same? Because this supply voltage remains same. Actually V Thevenin is a function of supply voltage. So we need to consider the value of V Thevenin before we need to consider the source voltage before determining the value of Thevenin voltage. It is a function of Thevenin voltage. Okay. What I mean to say overall, if you are getting confused, the Thevenin voltage will always depend on the supply voltage. Since supply voltage is held constant, the Thevenin voltage will also be constant. Now that I know the Thevenin parameters for the 10 volt DC, now it is saying it is exciting the network with a 6 volt DC at port A. That means we have changed the supply voltage, which means the Thevenin voltage is bound to be changed. It is giving me the information that 1 ohm connected at port B draws 7 by 3 ampere. See, the Thevenin voltage in a network depends on the supply voltage, but the Thevenin resistance, it is independent of the supply voltage. That is RTh will remain at 2 ohm always. That means I can calculate VTh dash as I into RTh plus RL. That is the new Thevenin voltage. It is saying it is drawing a current of 7 by 3 ampere for a load of 1 ohm. So it is 7 volt. So the new Thevenin voltage is 7 volt. So what I can say is V Thevenin is 9 volt when Vs is 10 volt. V Thevenin is 7 volt when Vs is 6 volt. Okay. So that means, and it is saying it is a linear network, that means V Thevenin depends linearly on the supply voltage. So what I'll say is V Thevenin is AVs plus B. Okay. So what I can say, 9 is equal to 10A plus B and 7 will be equal to 6A plus B. If we subtract these two equations, what I'll get is 2 is equal to 4A, or we can say A is equal to 0.5. Similarly, what will be the B? B will be 4. That means it will be 0.5 into Vs plus 4. So Thevenin voltage is given by 0.5 Vs plus 4. Now it is asking if 8 volt DC is connected to Vs or it is connected to port A, what is the open circuit voltage at port B? Open circuit voltage is actually Thevenin voltage. So VOC is equal to VThevenin. When supply is 8, it will come out to be 8 volt. Okay. So that is how sometimes it may not appear to you, but the Thevenin equivalent may be asked indirectly. Here there is no word written as Thevenin or a Norton, but you have to identify that we have to use the Thevenin equivalent. Let us look at the next part of the same problem. It is saying with 10 volt DC connected at port A, what is the current drawn by 7 ohm resistance? What will be VThevenin? It will be 9 volt because Vs is 10 volt. Okay. Then I know VThevenin is equal to I into R Thevenin plus RL. VThevenin is 9. I need to calculate. R Thevenin is 2. And RL is 7. So I will come out to be 1 ampere. Moving on to the next problem. It is asking in the lattice network the value of R for the maximum power transfer to the load. If you want to transfer maximum power to the load, then you have to keep R same as the Thevenin resistance. For Thevenin, what we do is, we will make the supply equal to 0. We will short circuit this terminal. If we short circuit this terminal, then look at this resistance 7 and the 5 ohm. They have one terminal common and other is common due to this shorting. So they both are connected in parallel. So R1 will be 7 into 5 by 12, that is 35 by 12 ohm. Look at the other resistances 6 and the 9. R2 will be 6 into 9 by 15. Then it will be 54 by 15, that is 18 by 5 ohm. Okay. Then what happens is, these resistances will be connected in series. Okay. Because if you open circuit this load, if you disconnect this, then this network is actually like this. These two are in parallel like this, and these two are also connected like this. So when we replace it, we will get two resistances which will be in series, because we need to find the resistance across, let us say, AB. So both will be in series. So how much will be the equivalent resistance? Now these two resistances will be in series, that is R equivalent will be R1 plus R2, that is 35 by 12 plus 18 by 5. 35 by 12 comes out to be 2.9167. 18 by 5 will be 3.6. So it will come out to be, equivalent will be the sum of the two. It will be 6.5167. Okay. So whenever you are calculating the Thevenin resistance, do not forget that you have to short circuit the voltage source and open circuit the current source. In our next problem, it is saying, if Rg in the circuit is shown is variable between 20 ohm and 80 ohm, what is the maximum power transfer to load RL? Now the thing is here, the power transfer to RL will be I square RL. Okay, you cannot directly apply here maximum power transfer, because there I told you one necessary condition, that the load resistance must be variable. Here the load resistance is fixed. If RL is fixed, then power will be maximum if current is maximum. Okay. So to maximize the current, we know that current is equal to actually V upon Rg plus RL. To maximize the current, we have to minimize the resistance, and we can minimize the value of Rg to 20 ohm. So what will be the maximum current? 40 by 20 plus 60, that is 0.5 ampere. So what is maximum power transferred? 0.5 square into 60, that is 15 watt. Okay, this way you have to tackle this problem. Remember, we apply maximum power transfer theorem if and only if the load resistance is variable. In the next problem, it is asking the equivalent of the circuit given in the figure. As you can see, it has multiple branches. That means I'll apply Millman's theorem. So if I calculate equivalent voltage, it will be V1 by R1, V2 by R2, V3 by R3 divided by 1 by R1, 1 by R2, 1 by R3. So V1 by R1, V2 by R2, V3 by R3 all are V by R. And these resistances are also equal, so it is 3 by R. It will come out to be V. And what about R equivalent? It will be parallel combination of R, R and R. So it will be R by 3. So the equivalent circuit will be plus minus V, then R by 3. Okay, this will be the equivalent of the given circuit. In our next problem, it is asking the current I2. Now if you see, we have been given two network topologies in which we have exchanged the excitation and the response. Here excitation is at the first terminal, here excitation is at the second, here response is at the second terminal, here response is at the first. Now by reciprocity theorem, what I can say, ratio of response to excitation must remain same. So here 7 by 4 must be equal to, if you see, the polarity of voltage has been reversed also, I2 by minus 30. So I2 will be 7 into minus 30 by 4, that is minus 210 by 4, that is minus 52.5 ampere. Okay, so whenever applying reciprocity theorem, do take care of the polarity of the supply also. If the polarity is reversed, you will have to consider it with a negative sign. Let us move on to the last problem. It is saying in the circuit shown, we need to find the missing branch voltage and current. Then we have to calculate power absorbed by each element and then find the total power absorbed. So let us do our first objective, that is to determine voltage and the branch current. So to determine branch voltage, we will use KVL. If we use KVL in the first loop here, then I'll say V1 minus V2 plus V3 must be 0. Now V1 is 4, V2 is 2. 4 minus 2 plus V3 is 0. That means V3 is minus 2. So let us write down separately. V3 is minus 2 volt. Okay. Next, let us apply KVL in the second loop. So what we will say? Minus V3 plus V4 minus V5 is 0. Then minus V3 means we have just determined 2 volt. V4 means 3 minus V5 is 0. That is V5 is coming out to be 5 volt. Okay. Then let us apply KVL in the loop number 3. Like this. So what we will say? Minus V2 minus V6 plus V4 is 0. Now we know minus V2 is minus 2. V4 is 3 is equal to V6. So V6 comes out to be 1 volt. Okay. So these will be the branch voltages, minus 2, 5 and 1 volt. Now let us apply KVL in the third loop. What we will write? V2 minus V6 minus V4 is 0. So V2 is given to me as 2. V6 is unknown. V4 is given to me as 3. So V6 comes out to be minus 1 volt. So now we have all the branch voltages V1, V2, V3, V4, V5, V6. Now we need to find the branch currents. To determine branch currents, we will apply KCL. So let us first apply KCL at node number 2 here. So the outgoing currents are I1, I2 and I6. All are outgoing. So the sum must be 0. That is 2 plus 4 plus I2 is 0. So I2 comes out to be how much? Minus 6 ampere. Okay. Then let us apply KCL at node A. So here incoming current is I3. Then incoming is I4. Then incoming is I2. All are incoming. The sum must be 0. I3 is 4. I2 is minus 6. So I4 comes out to be 2 ampere. Next, let us apply at the next node, at node 4. At node 4, outgoing current is I4 as well as I5 is also outgoing. But incoming current is I6. I4 is how much? 2 ampere. I5 is how much? I5 we haven't yet calculated. I6 is how much? I6 is also 4. So I5 will come out to be 2. Okay. So that now we have all the branch currents also. I1, I2, I3, I4, I5, I6. Now we need to calculate the power absorbed by each element. That means first we will calculate P1, that is V1 into I1, 8. P2, that is V2 into I2. V2 is 2. I2 is minus 6. So minus 12. P3. V3 into I3. V3 is minus 2. I3 is 4. Minus 8. P4. V4 into I4. I4 is 2. Into 3. 6. P5. That is V5 into I5. V5 is 5. I5 is 2. So 10. P6. V6 into I6. V6 is minus 1. I6 is 4. So minus 4. So what is the overall power? It will be summation of all the powers. Collect the positive term. 8 plus 6, 14 plus 10, 24. Minus 12, minus 8, minus 4. That is 24. It is 0. Which is in accordance with the Talighan's theorem. That overall power absorbed by all the elements in a network must be 0. Okay. So that is how Talighan's theorem is always applicable. So most important theorems that we have learned from the gate point of view are superposition, Thevenin and Norton, and the maximum power transfer. From there majority of questions are framed. This Millman's theorem, Talighan's theorem and reciprocity. These are actually useful in helping you out throughout the rest of the course and not so much for the direct problems based on these theorems. Okay. So I'd recommend that you practice Norton's and the Thevenin's theorem the most. Hi guys, In the last lecture, what we covered was, we covered superposition theorem, in which I told you if there are multiple sources in the circuit, then what you need to do is calculate the response using each and every source and then just take the linear combination of those responses. Okay, that was always applicable for a linear network. A linear network has two properties. It follows the property of homogeneity and superposition. Then we went on to study about Thevenin and the Norton theorem. Thevenin and the Norton theorem are very much alike, and the process that it involves to find out Thevenin and Norton equivalent is almost same. So basically Thevenin equivalent consists of a open circuit voltage and Thevenin resistance. Norton theorem consists of short circuit current and Norton resistance, and actually Norton and the Thevenin resistances are same. Okay, so R Thevenin is equal to R Norton is equal to VOC by ISC. Then I explained to you how to tackle each problem. One with the independent sources, second with the dependent sources, and third one with the both. Okay, and we also saw that the Thevenin and the Norton equivalent can be obtained from each other just by the source transformation technique. In this lecture, what we will do is we will study some of the more network theorems that are helpful in simplifying the effort involved in calculating the response of any network. So the first theorem that we will study today is maximum power transfer theorem. In maximum power transfer theorem, I want to determine the conditions when the maximum power will be transferred to the load. Okay. Now basically, whenever any network operates, there are two criteria that you can usually follow. The two criteria are Pmax output, or the other is eta max. That is the maximum efficiency. Maximum efficiency means output power by input power must be maximum. Now usually the more famous of these criteria is the maximum efficiency, because even if you are deriving the maximum output, you do not know how much input you are consuming or how much power you are wasting. Okay, because what happens is, to derive the maximum output, actually the input power also goes up. Okay, so it is not an efficient utilization of energy. That I'll prove later on. But the thing is, maximum output power across the load will ensure that the load is working well and we have a high output. So let us see how to derive the maximum power output. So I have taken a simple circuit, one with a source voltage Vs, source resistance Rs, and the load resistance RL. Actually, we are varying the load resistance to determine at what values of load resistance will the power output will be maximum. Okay. Now this is a general circuit, because any circuit can be converted into this form by the use of Thevenin's theorem. Okay. If we apply Thevenin theorem, we can convert any circuit into a voltage source in series with a resistance. Now first let us calculate current in this circuit. It will be Vs by Rs plus RL. So what will be the output power? It will be I square RL, that is Vs square RL over Rs plus RL whole square. Now to have the maximum output, we will differentiate this function with respect to RL. So it will be Vs square can be taken as common, Rs plus RL whole square minus 2RL Rs plus RL. Okay. Equating the numerator to 0, what we will get is Rs square plus RL square minus 2Rs RL, sorry, plus 2Rs RL minus 2Rs RL minus 2RL square is equal to 0. This gets cancelled out. and we get Rs square is equal to RL square, and if we take square root we will only get positive values because resistance is positive. Okay, so whenever the load resistance is same as the source resistance or the Thevenin resistance, then we get the maximum power output. In this condition, what is the output power? P out will be Vs square over Rs plus RL square, means 4 Rs square into Rs, which is Vs square by 4 Rs. Now what is the input power? Vs Is, which is equal to, Vs is how much? Vs. Is is Vs upon 2 Rs. That is Vs square by 2 Rs. That means what is the efficiency? It is 50%. So, under maximum power transfer condition, half of the power is transferred to the load and the other half is dissipated as heat in the network, or that energy is lost. That is why maximum power transfer condition is not so desirable from a practical point of view, because the losses are also very high and such low efficiency in a network is unacceptable. Okay. Now, where can you apply this theorem? First of all, you can apply this theorem wherever the load resistance is kept variable. Okay. If load resistance is kept fixed, then this theorem cannot be applied. How to apply this? First, you have to convert any network into Thevenin equivalent, and then you will say the load resistance must be equal to Thevenin resistance in order to have the maximum power in the load. Okay. And as we have seen here, the efficiency is 50%, which implies only 50% of the input power is transferred to the output. Is it fine? And this theorem is independent of source and the load impedance and the voltage and the current sources. Here just we need to concentrate on the Thevenin or the Norton resistance. No need to worry about the sources in the network. Always the efficiency will be 50% and the load resistance must be same as the Thevenin resistance. Let me illustrate this concept by use of a problem. Here if you see, we need to find the value of load resistance so that maximum power is transferred to it. So that means we need to calculate first of all the Thevenin resistance. To calculate Thevenin resistance across A and B, we will have to open circuit these terminals. And what is the network that we will get is, okay, network will be like this. So what we will do is, since it is open circuit, we will take two loop currents, let us say I1 and I2. Now if we apply KVL in the loop number 1, it will be 20 is equal to 3I1. So it implies I1 is equal to 20 by 3. Similarly, it is 3 ohm, 4 ohm. KVL in loop 2 will come out to be 20 by 7 I2, which implies I2 is 20 by 7. Now based on the current, we can mark the polarity plus minus, then plus minus. Okay. So this current will not be like this. It should leave the positive terminal actually. This should be I2. Remember always the battery will deliver power, so current must come out of the positive terminal. So this will be plus minus. That means what will be the output voltage? It will be, this is 2 ohm, 2I1 minus 4I2. 2 into 20 by 3 minus 4 into 20 by 7. So how much will it be? 40 by 3 minus 80 by 7. 40 into 7 minus 80 into 3 by 21. That is equal to 40 by 21 volt. Okay, it is 280. This is 240. So 40 by 21. So that is the open circuit voltage. Now we have to determine the Thevenin resistance. For that purpose, we will short circuit this voltage source. Now what will happen is, if we want to find out the resistance, this resistance and this are in parallel. 2 and 1 in parallel will give me 2 by 3. 4 and 3 are in parallel. It will give me 12 by 7. And both will be then connected in series. So 2 by 3 plus 12 by 7 will give me 14 plus 36, that is 50 by 21 ohm. Now that means for maximum power transfer, the load resistance must be equal to 50 by 21 ohm. So let me draw the Thevenin network. 40 by 21, 50 by 21 RL. So for maximum power transfer, RL will be equal to, then what is the power transfer to the load? It will be 40 by 21 square divided by 4 into 50 by 21. 1600 by 200, it will give me 8 by 21 watts. So this will be the maximum power transfer to the load. The next theorem that we study is known as reciprocity theorem. Reciprocity theorem means the network is reciprocal. What is meant by the term reciprocal? It means that if we change the terminals of the response and the excitation, their ratio remains the same. Or we can say the ratio of response to excitation at the two terminals should always remain the same. Okay? And in what conditions it must remain same? In case you interchange the position of the response and the excitation. Like if you see here, I have applied the excitation at the left hand side of the network and response is taken at the right hand side. Okay. So the ratio will be response to excitation if you take I2 by V1. Or you can understand this is node number 2, node number 1. Now if we have applied the input at node 1 and taken the output at node 2, the ratio will be I2 by V1. Now interchange the excitation and response. That is, apply the excitation at node number 2 and take the response at node number 1. Then their ratio will be I1 by V2. That is response by excitation. So it will be, the reciprocity theorem states that I2 by V1 is equal to I1 by V2. Okay. That is, the ratio of response to excitation will remain same. Is it fine? But the condition is it must have only single source. That I'll tell you how. But this network must only have a single source, then only this theorem can be applied. Secondly, all the elements must be linear. That is, we cannot use analog devices like BJT, like a diode, because those devices have exponential characteristics and not the linear characteristics. Is it fine? And there must be no dependent source. That means in case there is only one source which is dependent, this theorem will not work out, because actually the dependent sources need an independent source to energize. So if I give you a network which only has one dependent voltage source, then this theorem cannot be applied. Is it fine? So now let me show you how this theorem has been derived. This theorem basically rests on the impedance and the admittance matrices. Now first let us understand impedance matrix. Now an impedance matrix gives the relation between the node voltages and the node currents. Let me assume 3-bus system or 3-node system. It will give a relation like this. I1, I2, I3. So basically these are the node voltages and these are current source at each node. Now if you see here, if I write out any equation, let me say V2, it will be Z21 I1 plus Z22 I2 plus Z23 I3. Now equate all the currents to 0 except, let us say, I3. Then what I will get is, if I1 equal to I2 equal to 0, there is only one source, that is I3. That is V2 is equal to Z23 I3. Then what is the ratio of V2 by I3? It is Z23. Okay. And similarly, if we write down the equation for V3, it will be Z31 I1 Z32 I2 plus Z33 I3. Equate now I1 equal to I3 equal to 0. So V3 is equal to Z32 Z32 into I2, which implies V3 by I2 will be Z32. Now a special property of the bus impedance matrix is that it is symmetric, that is Z23 is equal to Z32, which implies V2 by I3 is same as V3 by I2. That is our reciprocity theorem. So reciprocity theorem is derived from the basic that the impedance and the admittance matrices are symmetric. What is the admittance matrix? It is just the inverse of impedance. That is I1, I2, I3 will be equal to Y11, Y12, Y13, then Y21, Y22, Y23, and then Y31, Y32, Y33 into V1, V2, V3. This matrix is also symmetric. Actually, it is inverse of the Z matrix. Is it fine? So based on this, we have derived this reciprocity theorem. Okay. And whenever you are writing the reciprocity theorem or you are deriving the reciprocal network, current source must always be connected in parallel, whereas the voltage source must be in the series. Remember this if you are deriving the reciprocal of any network. Is it fine? So what does reciprocity theorem states? It states that if we interchange the terminals of the response and the excitation, then the ratio of response to excitation or excitation to response is identical. Next theorem comes is Tailligand's theorem. Tailligand's theorem states that sum of instantaneous power absorbed by all elements in all branches of network is equal to 0. That is, sum of P absorbed at any instant is 0. Now how can I say this? I can say this because any network or any system has two type of elements. One will be the source, other will be the load. Okay. So the sources that are generating power, that will be transferred to the load. And by law of conservation of energy, generated energy will be equal to consumed energy. So power absorbed by all the elements will be 0. Okay. Now you might be thinking only the loads will be absorbing power. Then how come the power absorbed by all elements is 0? The thing is, sources are delivering power. So I can say they are absorbing negative power. Okay. So the amount of negative power absorbed is same as amount of positive power absorbed. So that net absorption is 0. The sources are delivering power, that means they are absorbing negative power. So amount of power they deliver or amount of negative power they consume, same is should be consumed by the load, that is it will be same as the amount of positive power consumed by the load. Is it fine? So this is written something like this. I is equal to 1 to B, Vi, Ii must be 0, where B is the number of branches in the network. Okay. That means if we multiply the voltage of any branch with the current in that branch and sum up over all the branches, it will come out to be 0. Is it fine? So this is based on just the law of conservation of energy. And it is always applicable no matter what is the network, no matter what are the type of networks, and what is the value of each and every element. Okay? Because in any network, whether it is linear, non-linear or anything, the power or the energy will be conserved because energy can neither be created nor be destroyed. Now, how to take a convention whether the energy is power is positive or power is negative, or whether power is delivered or absorbed? See, if we talk about sources, now suppose there is a voltage source V. If current comes out of the positive terminal, then it delivers power or it absorbs negative power. If current goes into the positive terminal, then it absorbs power. What about a load? In a load, positive negative are like this. If current travels from positive terminal to negative terminal, it absorbs power. But you can say it invariantly that whenever there will be a load, it will always consume power. A load can never deliver a power. Like a resistance can only consume the current in order to convert the electrical energy into heat energy. It cannot deliver the energy to the rest of the network. Moving on to our last theorem, it is the Millman's theorem. Basically, a Millman's theorem states how to convert multiple branches of a circuit into a single branch. Like if you see here, in the original network that we have multiple voltage sources in series with multiple impedances like E1 Z1, E2 Z2 and En Zn. But solving this network will be cumbersome because there will be a lot of loop equations involved. So it would be better if I can convert this all branches into a single branch with EMF E and impedance Z. Now, how to do this is, we will apply here Thevenin's theorem. So what you do is, first of all find out Z Thevenin. For that, what we will do is, we will short circuit these sources. Then all these impedances will be in parallel. So it can be written as 1 upon 1 by Z1, 1 by Z2, plus 1 by Zn. Now reciprocal of admittance can be written as reciprocal of impedance is admittance 1 by sigma yi. Okay, because 1 by Z1 will be Y1, 1 by Z2 will be Y2. If you do not yet know the concept of admittance, basically it is similar to what we study about conductance. If resistance is written as rho L by A, then conductance is given as 1 by R, which is sigma A by L. Sigma is the conductivity. Okay. If resistance represents the opposition to the flow of current, conductance represents the support to the flow of current, or how easily can the current flow through a material. Okay. So this will be Z Thevenin 1 upon summation I is equal to 1 to N Yi. Now let us calculate the short circuit current. Why I am calculating short circuit current? Because the open circuit voltage can be written as short circuit current multiplied by R Thevenin. If you short circuit these terminal, each voltage source will supply the current to it. So what will be short circuit current? E1 by Z1, E2 by Z2 up to En by Zn. There will be no current flowing between the two voltage sources, and the entire current will flow into the short circuit because current always tries to take the path of minimum impedance. So if I want to find out E Thevenin or E, which is in this case it will be E1 by Z1 plus E2 by Z2 En by Zn multiplied by summation, or rather 1 upon summation yi. So I can write E as summation ei yi divided by summation, or divided by summation, we can say yi. Okay, that will be the net EMF, and that is basically the statement of Millman's theorem. Is it fine? Similarly, if we apply the Norton's theorem, we come to a theorem called as dual Millman's theorem. In this, what we do is we basically apply Norton's theorem. Here what we are trying to do is we are trying to convert multiple current sources into a single current source. Now if we are applying Norton's theorem, what I'll do is I'll first find out the equivalent impedance. Now to determine equivalent impedance, we will open circuit the current sources. Then all these impedances will be in series. So Z Thevenin will be equal to Z1 plus Z2 plus Zn, that is summation I is equal to 1 to n Zi. Now to calculate the overall current, what we need to do is we will find the open circuit voltage. In case of open circuit, none of the current will flow between the terminals AB. So what is the voltage here? The voltage across AB will be I1 Z1 plus I2 Z2 plus IN Zn. Then what will be the short circuit current? It will be open circuit voltage by Z Thevenin, that is summation II Zi over summation Zi. And what is this Z? This Z is basically series combination of all the Zi. So that is your dual Millman's theorem. Okay. These theorems are just application of Thevenin's and the Norton's theorem and help us combine multiple branches of the network into a single branch. So let me summarize what we covered in this lecture. We first saw maximum power transfer theorem. The maximum power transfer theorem helps us identify a condition in which maximum power is transferred to the load. In that case, we saw it is V Thevenin square over 4 R Thevenin. Okay, and we saw efficiency is 50%. Then we came to the reciprocity theorem, in which I told you if we interchange the terminals of the response and excitation, the ratio of response to excitation will remain same. Then we came to Teligens's theorem, in which I told you sum of instantaneous power absorbed by all the elements is 0, because the power generated by the source will be same as power consumed by the load. And last we looked at the Millman's theorem, in which we combine multiple sources into a single source so that the analysis can be simplified. And if we apply Norton's, it is converted to dual Millman's theorem. Okay. So these are all the network's theorems that are there to simplify our effort in solving any network. In our next lecture, we will see a few problems based on the network theorem.